Hey Sager, how are you?
Hiya, I'm great, thanks. You?
I'm cool. Nice to see
No
you
Thursday
around
today,
here.
so I'm great. Yeah.
So let's hope that by next year we will manage to meet in person again
Yeah,
somehow.
that's a good plan.
Yeah, because this remote thing, I mean, it works, but it's not quite the same.
Yeah. Oh, getting used to it right now.
Yeah, that's actually my fear, that people
Yeah,
will get
that's the
used to
problem.
it.
Yeah.
Yeah, and then people won't want to travel anymore. But we'll see.
That's not going to happen.
Yeah, let's hope. Hi, Florian. Buenos días. So we will be starting in about 10 minutes. So now I'm inviting presenters in case you want to test and check that your audio and video are working properly. Now it's the time to do so. Hi, Florian.
Hello, can we check the presentation mode?
Yeah, sure. Let me make presenter. Yeah.
Okay.
Okay, I'm gone. I think that I'm taking presenter again.
I couldn't
So I
find
can
the way
select.
to switch the slides.
It is the plus symbol, but I'm doing it for you. This would be.
They are each numbered, so it should be number 1. Should
Oh, awesome. Yeah. Okay, Florian, I'm making you presenter again.
Ah, okay, it's the old version of the slides, but that's fine.
Uh-oh.
Oh,
Well,
you sent me new ones?
I uploaded new ones yesterday.
Did you send them through to me on an email? If not, it will be whatever you emailed over to me.
Okay, no, I think I can use those. It's just.
but there is time. There is time to upload to the new version.
Yeah.
Okay, then.
So I
can
think.
I up?
Oh,
Can I
I think you should be able to do so. Yeah.
This is really confusing. I should have. Where's the button for there's the zoom button.
So if you press the little blue cross in the corner, and then it should say something like manage slides or manage presentations, and then it should come with like a box, and then if you drag the file into it, it'll upload it and it'll automatically launch that as well.
This looks great. It's doing something.
Uh-huh.
So the slide title now matches the session title, which I think is a slight improvement.
Awesome. So are you happy?
I am happy. So this looks, yeah.
Cool. So Andrew, do you want to test your audio video?
Can you hear me all right?
Yes.
How about the video?
It looks awesome.
Good. I shall get that reframed by.
Okay, let's see the slides.
Oh, well, I'm not up for another. Don't confuse everybody. I'm not up for another half hour.
There you go.
Okay.
Just if you want to test everything.
Okay. Do you want to? I do have a YouTube thing in the middle of it. Do you want me to test that?
Yes, just in case the demo gods are not on your side.
Well, that's the point of the YouTube. Share an external video. Copy, get shareable link. I have 4 demos. Seems to be working. I don't need to ruin it for everybody.
Yeah, but it's making echo with your microphone, so remember to switch off, to mute yourself while you're playing the video.
Today to simple ones, one each for OpenATC and
Yep,
Open.
perfect.
Perfect. Perfecto. Oh, mute.
Okay, I just wanted to figure out how to make the video go away. Yeah, no, I did not want to do a live demo, for many reasons, not least because I have to lock the device I'm doing the demo on, and it's quite possible that the automated testing the CI system has already locked it.
Yeah, well.
But so it's in the video. It's not exactly a dynamic experience, I'm afraid.
You wanted to avoid the segmentation fault party, right?
Sorry?
You wanted to avoid the segmentation fault fest. That's
Well,
what live demos are.
Yeah, it's not so much that as what if the drivers have updated themselves, or the or the CI system has locked the board, or yes.
So many funny things can happen, right?
Yeah, and also this way I know how long it's going to take.
Okay, so Jan, are you around? I don't know if he's locked. No, he's not around. Okay. So we are starting in 4 minutes. Hey, Mark.
Sorry,
Why?
I don't know. Wrong button.
Okay. Okay, so I'm taking presenter again because I have to go through the LPC slides. Default. There you go. Two minutes to start. All right, so it's o'clock in my watch, so let's start. Welcome everybody to the last day of the GNU Tools Track. So now I'm supposed to go through those slides here, which is basically sponsors, Facebook, social network, making friends, IBM, mainframes, ARM, Microsoft, Amazon, Netflix, Red Hat, Collabora, VMware for the t-shirt sponsor. I have not seen the t-shirt yet, so I don't know if thanking them or not. And the Linux Foundation for the conference services, which, by the way, are working very, very well. Like last year, it's very impressive. There is an anti-harassment policy, so I'm sure everyone read it in detail. Just be nice with everyone. Housekeeping, okay, this is the 4th day of the conference, so I assume everyone is aware of this as well. Otherwise, look at the slide. The planning committee of the conference, thank you very much to all of you. I know how painful it is to organize events, so we really, really appreciate. And that's it. So Florian.
Yes.
So let me see, where are you? Here you are. I'm making you presenter. And let us know how we can remove implicit declaration, function declarations in C. I'm very interested. Thanks.
Thank you. So I'm going to talk about implicit function declarations, and I will try to make this presentation very short so that we can have a bit of a discussion in the allocated time. So what are implicit function declarations? So what I'm showing here is basically K and RC, so from the 70s probably. And as you can see, there are no keywords here. And the curious thing is that even though there are no includes, no keywords, it's still syntactically valid C. And even today, with GCC's defaults, it compiles. The compiler produces lots of warnings, but it compiles and it links. And if you're on 32-bit and a 32-bit architecture, then it will likely run as well. Even though we didn't provide any correct prototypes or includes or even a return type for main. So why is this a problem? Implicit function declarations on 64-bit architectures are particularly painful because the implicit declaration that is generated if you refer to an identifier using a function call syntax, this automatically generated declaration doesn't have a prototype, and its return type is automatically set to int. So for example, for the getInt function, you get an int return type instead of a pointer. And the x86 64 ABI is such that if you use that value in like printf, then the other 32 bits are required to be discarded and set to 0. So the pointer is likely not valid anymore, and you get a crash at runtime. That's pretty obvious, I think. What's slightly more confusing is if you have a function that returns a bool result, then x86 64 has a special ABI for that, and only 8 bits of the register are significant. So if you look at that register as an int, then yeah, your Boolean checks still look like, the compiler will accept them and warn about the implicit declaration, but it's not likely that you get the right result. And one thing that I realized when hearing the presentation on the M1 new Apple AH64 ABI, the lack of a prototype means that all functions are variadic. So this only works if your API for arguments which are passed on the stack, you basically have promote them to to a type that looks like a full register, basically. Otherwise, you can't get interoperability without having the correct prototype. And I think for the PB664LE API, that actually was a consideration. Maybe they would have liked to do it differently, but yeah, why can't? And I want to show why this is a difficult problem now. So one thing that makes this a little bit more annoying even is that if you link a shared object, you can actually have a successful link, and the library can be loaded at runtime successfully if you lose lazy binding. And this means that you never actually get any diagnostic unless you actually manage to run the binary and execute the right path during testing. And this is not very well known, unfortunately. So this we made some changes to OpenSSL. We basically switched from 1.1 to version 3.0, and as part of that, some functions were removed. And what happened is that we were actually able to build .NET, the .NET Core runtime successfully, but the result was a corrupted binary, a slightly corrupted binary, because it referred to the OpenSSL function that was no longer there. And even though the build succeeded, part of it was broken. And I raised this with the OpenSSL developers, and they didn't realize that the toolchain default on GNU Linux is actually to have both lazy binding and implicit function declarations enabled in the compiler and linker. So even if OpenSSL developers didn't know that, and it's difficult to see that how people who run smaller projects to get this right. So the question is, what can we do about this? So we can tell developers to build with this additional warning and warning flag and turn the warning into an error. That should be easy, but again, it's difficult to reach all the developers. So we probably should make the switch in GCC itself. But we can only do that right now for new programs, because we have tons of existing autoconf checks that have implicit function declarations in them. And if the configure test fails, not because the feature is missing in the platform, but because there's an implicit function declaration, you lose that feature in the build. And because autoconf is magic, it automatically disables the test suite bits for that. So you still get a consistent build result, but the feature is gone. And this is not entirely unusual, even for large and important projects. GCC itself had an issue. This is how this looks like. This is a autoconf fragment. And what is missing here is an include directive for unistandard.h, because that is the header that includes the syscall function prototype. sys/syscall.h does not actually include the prototype, only the constants. And this is basically a reason why it's so difficult to fix as well, because you have to go into this old autoconf fragments and add missing includes. And then for stuff that's supposed to support really old platforms, you don't really know if they have all the standard header files. So obviously we know that Linux has unistandard.h, so that's easy to fix, very easy to fix. But if this were an old configure check that's supposed to run on Sun S4 or something like that, then you really don't know if they have the full complement of current POSIX headers. Probably not. So this is why I say that enabling this at the distribution level is hard. So if we just flip on the switch and build a distribution with that, with those warnings as errors, then we get quite a bit of different resulting binaries, unfortunately. And builds even succeed. So it's not just that the build fails, but you get a successful build and the result has different features. So we made a couple of attempts to get this done in Fedora. The latest attempt uses the first the 0th attempt, so to speak, was just to enable it in the compiler flags, and that sort of crashed and burned across the distribution. That wasn't really nice. The first real attempt was doing config log config.h diffing, and that was implemented by Jeff Law in one of his test builders. Yeah, and this doesn't really work for all packages because not everything uses autoconf that has problems with this change. And I'm now contemplating to put patch GCC into the build root, into a special build root to build a distribution, and for each package, look at the end of the package build whether a directory that gets populated with these error nodes is still empty. So if we ever run into an implicit function declaration during the build process, we can detect this at the end of the build, even if the build system itself ignored the build failure. Yeah, I haven't run this yet. I just want to see if there's support for this. And there's unfortunately, even if we have these, if we do this in Fedora, it's not actually easy to share the results with the rest of the world. One reason is that this seems to correlate a lot with old code bases, with old build systems, and those tend to have upstreams which aren't particularly active. So if we've patched that in Fedora and have our patch, then it may not be easy to make sure that everyone gets these patches before we switch the default in GCC upstream. On the other hand, it's not really interesting work fixing those packages, but yeah, I think we all have these days where we don't feel like doing really creative stuff. So yeah, gloomy November days it is probably for this. And one thing that surprised me is that Apple actually made the transition, but they didn't fix too many upstream projects. So homebrew users are currently screwed, I suppose. And what I didn't realize is that this is due to the probably due to the new Darwin AX64 ABI, which can't really do implicit function declarations anymore. But I think I still, my personal opinion is that we should do this, and the improvement in development experience is real, especially the Boolean function result mismatch tends to confuse people, and they come to us and think that we have a compiler bug, and giving a clear diagnostic where we can actually do that and not have just a warning that scrolls by and is missed by the developer would really help people here. So I think it's too late for GCC 12, but we might be able to do it for GCC 13. There are some questions about mechanics, like I don't think we should tie it to the standards version. We should enable it for C99 and later standards, because that matches what ISO says, and probably have a separate -f flag to control the behavior. I think it's not really great to have a warning for this like we do today, and enable W error for this warning by default. It doesn't sound very consistent to me.
Yeah, that's completely wrong to enable W arrow by default. That's
Yeah,
yeah.
that's what Apple did in their Clang
Yeah.
downstream.
It's fine to make it as an arrow by default. It already is a warning by default.
Yeah.
Without any warning flags, right? And it has been for quite a few years, I think. I'm not sure actually. I didn't check. And that's probably the reason that Apple didn't see many problems, because most people actually do look at the warnings, or enough people to look at the warnings.
But not for configure checks.
Not for configure checks, no.
Yeah.
That's
And that's the problem we have on the distribution level. And I think that's the problem that Homebrew also has.
so. How can we fix it in the configure checks?
Well, what if AC init would change the flags, the compilation flags, to disable the error?
During configure or?
Yes, AC init, the beginning.
The problem is a lot of the configure files that are out there can't be regenerated. We ran into this with LTO as well. Yeah, it sounds like such an easy path, but it doesn't actually work.
Yeah, good point.
Yeah, and there are also build
but
systems that don't use configure.
Yeah, that's one thing you highlighted, Florian, is the test we did before, they massively failed. They showed how big this problem was, but they didn't touch any of the systems that don't use autoconf. That was the only stuff we tested. It's a fair amount of the distro, but there's still a lot of things out there. It's a mess.
As you found out, implicit function declarations do not actually work with all APIs.
Nope, they don't.
Yeah.
I think the idea of essentially packing up compiler so that we can store these things away as kind of a side effect of running GCC, and then post build looking for those artifacts. That sounds pretty viable because it's independent of autoconf and the build system. Essentially, anything that calls GCC is going to create these things for us and allow us to find all these problems. So I like that, Florian. And so the question is, once we get that data, and I think it's, as you mentioned, Florian, it is highly correlated to old, practically dead projects. How do we coordinate?
Sorry, your audio.
Red Hat's engineers do some, SUSE's engineers do some, Ubuntu's engineers do some, and we end up duplicating a ton of effort.
So would it be viable to detect this autoconf that we're running?
It doesn't really solve the problem though, because it's bigger than autoconf.
Yeah,
Autoconf is just what we saw in our first round of testing.
Yeah, and I think that's what makes Florian's idea of hacking up the compiler so that it can record when it sees these implicit calls without a prototype, and having that be stored by the compiler solves that problem. It allows us to get the data we need across every build. I like that. I just worry about, all right, once we've got the data, we start fixing these things. I don't want to see duplication across the distros. And then how do we engage these upstreams that are practically dead? Because we're going to end up fixing it.
Yeah, the only thing I can think of is creating an organization on GitLab or GitHub or one of the other source code sharing sites and start putting repositories there with the patches on top.
Yeah, I guess if we get a rep from Ubuntu and a rep from SUSE and a rep from Fedora and anybody else that wants to leverage off this work, I think that's viable, and it's probably the best solution given the state of the packages we're likely looking at.
Yeah.
In fact, we probably should have did that for the LTO transition. in retrospect.
Yeah, I think it's harder there because, yeah, I don't know.
Yeah.
Detection for LTO or LTO-induced failure detection is actually harder for autoconf and related feature.
Mhm. I'm well aware.
Yeah.
So Florian, when you activated you disabled the implicit declaration by default in RHEL, how many programs stopped passing the tests? Because you rebuilt the full distro, or?
When we did this first, I think that was in Fedora 26.
Okay, yeah.
What happened is that we broke the lib standard C++ ABI.
Oh, okay.
And then everybody ran away, I think. Said, oh my God, I don't want to do this.
Yeah. And then I think it was like 400 differences or something like that we could detect with just tester. And
It had to
is,
have been more than that because this hits autoconf really hard. Was that before we had? No, we must have had the config.h diffing in there for that test.
yeah.
Maybe. So is it possible, Florian, that those 400 were packages that weren't regenerating the autoconf configure scripts?
No. I think it's not extremely widespread. It's basically 5% or so of the distribution that needs fixing. That's my.
I thought it was worse, but you're closer to this, so I'll take your word. 5% isn't terrible.
It's still. I mean, it's still a lot.
It's still a lot of packages.
And some of this stuff is really hard to fix. I looked at unzip, I think, fixing unzip. I hope I get that right, and I couldn't do it. I mean, how hard should that be?
Yeah, I'm surprised.
And I couldn't figure out in the build system how to do that in a clean way.
Wow.
And basically make sure that it doesn't break any of the legacy targets that I couldn't test, obviously, like, I don't know, Data General Unix or something like that.
Relatedly, it would help a lot if we made W missing declarations the default. It actually finds problems pretty often. It warns when there's no header included that declares the functions you define. So it warns if it will not warn that you use a different prototype.
Yeah.
So is that possibly an intermediate step that we could possibly do for GCC 12?
Well, we could enable that by default for 12, of course, right? It's just a warning, so that's no problem.
I don't think that is useful, to be honest.
Yeah, that was my question, if that is useful for this.
Because it generates a lot of false positives. And
no, it generates 0 false positives. It warns when there's no declaration.
Yeah, but if you just compile one source file and then you could make these functions static, but
yes, or include the header for it. That's the whole point. If you write code without headers for the public functions you have, then you're asking for problems. That's what the warning is about.
Yeah, but then you basically invalidate all textbooks on C because that's how they start out, teaching people to write C.
Yes, but it's just a warning, and it's more than practice.
Still, I'm not sure if that really helps. And I think for the type safety issue that not sharing function declarations in a header, I think LTO is the better answer. And then you can check that the definition and the call side have both the same type. think LTO is, and that's what LTO is the answer for this, and that's what distributions are already doing. I think that was my 5-minute warning.
Yeah.
Yeah.
So is this something that Red Hat is likely to dedicate resources to tackling, Florian? Do you have a sense for that?
Basically, you told me not to pursue this like a year ago or two.
Yeah, well, I knew how painful this last slide is why.
Yeah, and I'm working on revising this decision. So.
And that's fine. It was really a matter of looking at what we had in front of us and saying, you know, what are the most important places to invest, and things change, you know, and we knock things off, and maybe it's a time to come back to this. And so that's why I asked the question. I no longer am part of that decision process.
Yeah. No, I'm going to make an internal proposal to spend resources on this.
Okay.
And
I assume that as a project would have no conceptual objections to cleaning this up. I can't see how they would. I can't see any place where they would reject the concept. What I could see them rejecting is the timing. But if we're talking about 13, we're far enough out that they're not going to worry about it yet.
Yeah, and I'm targeting 13 because then, at least for the active upstreams, distributions have a chance to pick up the fixes via upstream activity and releases. Yeah. It's too late for 12.
Oh yeah, way too late.
Yeah.
Well, as I said, I like the idea of having GCC leave a little artifact in the file system that you can go look for. That to me solves the how do you get good data problem. That will tell you consistently how big this problem really is.
Yeah.
The one, I thought at one time, and I don't know if the SUSE guys are online. I thought at one time the SUSE guys had a hack that changed flags when running configure.
Yeah, like
I know that doesn't solve. Yeah, I know that doesn't solve the whole problem, but it might get us. It might be enough to help us kind of identify what is outside of configure.
And you don't need the log file in any special way for anything except autoconf.
Yeah, I think you can treat compiling conf test.c differently from everything else.
Yeah, I thought they had a hack to do that.
Yeah. It's certainly attractive to do that. On the other hand, I feel like we should make the effort and clean this up properly.
Well, I'm not disagreeing about that. What I'm trying to figure out is are there ways we can start carving this up a little bit so that it's not a one-step transition?
Yeah, and you could combine the conf test C hack with the audit directory output.
Right, and so that gives you what are the source changes we have to that packages have to make versus what are the autoconf changes that we got to address. Exactly. Right.
Yeah, we need to log at the first. We also need to log the file name, obviously, and then we can see if it's conf test. Let's see. That should already cover that, and if it looks good, then except for autoconf, then maybe the conf test C hack is the answer for now.
This is Carlos. I would say I agree with Florian. There's investment that I think we can make in here to improve all this, which is why I think we're looking at this again.
And I will think about more ways to share the work and the work product so that the distributions have to do this alone. I think that's probably key about this.
Yeah, Yeah, and then we've got enough distro contacts that I think this is one of these cases where we have to work with everybody and see what we want to do.
Okay. Thanks everyone for the interesting discussion.
Thanks, Florian.
Hello. Right.
Oh, sorry, I was on mute. I was saying that okay, you must be able to select your slides using the blue plus button at the bottom left.
Right.
Now you are a presenter, so you must have access there.
Yeah,
there you go.
I can do it. Amazing.
Thank you. I will be collecting questions for you in the shared notes. Okay, for the end.
Okay. Let me make sure I can see them.
Don't worry about that. That will be afterwards if there is time for questions and answers. Okay, thank you.
Right then. So, debugging offloaded kernels on AMD GPUs. How exciting. Kernels cheer at once. So I'm just going to do a little preamble first, a couple of slides, and then get straight into the demo. I pre-recorded that, so it won't go wrong, I promise. That will last about 24 minutes, and then I shall go over some of the GCC-specific implementation notes that I gathered along the way. Just things of interest for those who care about such things. So about me, I am Andrew Stubbs. Hello. I started at Code Sorcery 13 years ago, and then we were acquired by Mentor Graphics, and now part of Siemens. So I still have my old one though, so I don't have a Siemens top yet. We need to get that organized. But we're still doing the same old business. For those of you who know the name from years back, it's just different bosses. Most recently, I've been working on the AMD GCN backend, for which I am co-maintainer. Also been contributing to the OpenMP and OpenACC for both GCN and NVPTX, and also the DeWolf support, for which we will be using in this demonstration. That is the GCC's DeWolf support, not the GDB's DeWolf support. That's the job of Rock GDB team. They are not in our team. This is developed by AMD as part of the Radiant Open Compute project. So they've taken the GDB and they have modified it so it can do heterogeneous debug. Tony, that's the name. Tony just talked about this on Monday, so if it's sounding familiar. It's basically GDB allows you to see both x86 and GCN code in one session seamlessly, and it's rather good. And we're going to demonstrate it. This works on, as far as I know, GCN 5 GPUs upwards. That may be oversimplistic, but I know it doesn't work on my GCN 3 ones that I have. So that's the Vega models onwards. If you install the Linux drivers to use the cards, the Rockham drivers, then you get the debugger as standard. It's squirreled away under opt Rockham, but it's there. And you can get this for Ubuntu, CentOS, Red Hat, and SUSE Enterprise, and probably other ones as well, but those are the ones that are officially supported by AMD and ROCm. These links take you to the generic ROCm page and the one specific to GDB if you wish to do further reading. The compiler I'm going to be demonstrating today is a development from the development branch, the OG11 development branch. We have better support for OpenACC worker threads and also the debug. All of this stuff is in the process of being moved to GCC mainline. The patches are submitted and being reviewed or being reworked. If you wish to build the development branch yourself, the instructions for building any compiler or any branch are there on the wiki. You have to go and build yourself an LLVM 9 install first, because that's the assembler and linker we use, and then you download the compiler and newlib and build and have fun. If you want binaries, the last GCC 11 official releases are available in a couple of Linux distributions. I'm aware of Ubuntu and SUSE. There might be one for Red Hat, but I don't have access to the package repo to have a look. Or easy access anyway. But those are not the development branch. They won't have much of this debug stuff. Hopefully the upcoming GCC 12 will have pretty much all of this stuff there, and then the official channels will have it. Right, so onto the demonstration. Here's one I made earlier. External video. Now this isn't the most dynamic. I do apologize, but it should explain everything. Over to past me.
4 demos today, 2 simple ones, one each for OpenACC and OpenMP, and 2 more interesting ones for OpenACC and OpenMP. So let's get started on the first one. VI demo 1. Here is our simple program. So this is the OpenACC example, and it is a very simple program. It doesn't do anything useful or interesting other than confirm that our device offloading really is working. This section in the middle, lines 7 to 14, are designed to run on the device, and the if statement checks to see whether it is on the device or whether it is running in host fallback mode. So if it finds itself in host fallback mode, this will return -1, and if it runs correctly, it will return 2 randomly chosen values. Nothing significant there. Right, let's get to the compiling. So this is using the compiler from the OG11 branch of GCC development. Not live. Some of these features are not in mainline just yet. It's very soon. So I have got OpenACC mode. I'm going to disable optimization and turn on debug info, and I'm going to switch to the GPU device that I actually have here, which is a GFX 908 device. Demo 1 is the source. Compile, done. Let's just check it works. B is 2 is the correct answer. So, debug it. Proc GDB, a.out. I'm going to switch to TUI mode so that you can see what's going on better, and because I like it. So here's our program, same as we just seen in the editor. I'm going to set a breakpoint on line 10, which is the first line in the device region, and a breakpoint on line 17, which is the first line on return to the host. If I do show you what the breakpoints look like, you can see that we have the host breakpoint there in main and the device breakpoint in main.ompfn0. This is because they appear to be as if it's a nested function within the main function, so it has a slightly different name. Okay, let's go ahead and run this thing. So we stopped on the breakpoint in the device. So at this point, GDB is interacting with the GPU and has paused the program running on the GPU processor through the ROCm drivers and whatever it is that AMD have done to work this magic. Now you'll notice that it stopped on thread 3. Let's have a look at what threads we have. We have thread 1, which is the master thread that we started on in main, exactly as you'd expect. Thread 2 is an internal ROCm thread. I don't know what it does. We don't care about it. We can ignore it. Thread 3 is running on the GPU device, and you can see that because it says AMD GPU here. We only have one thread running on the GPU in this example because there's no loops or anything. Obviously that's not going to be the normal case. Let's do info breakpoints again and see if it looks any different. So now you can see that breakpoint 1 has two instances, 1.1 and 1.2. 1.1 is the one that we had before, running on this host address, set on this host address, and 1.2 is the GPU instance of this function, and you can see that its address looks significantly different. And if we look at the program counter indicator on the TUI, we can see that it matches what was set. So we are definitely running on the GPU here. If I switch to thread 1, see what's going on over there. No source available. Where are we? Backtrace. We are deep down in some library code. Keep going. There we go. Frame 11 is main. Frame 11. There we go. So the main thread is effectively waiting patiently on this pragma. There's a bunch of libgomp and ROCm stuff going on that you don't need to worry about, but this thread is just set here waiting on this pragma for the device code to return. If I disassemble here, we can see that we have x86-64 machine code exactly as you would expect to see. And if I switch back to thread 3, and backtrace here, then you can see that just like running a thread on the host, there's no real history here. It's just entered at the point it was told to enter. We do have this artifact from an improperly terminated stack, but we don't need to worry about that. We just have the one function on this backtrace. If I disassemble here, by magic, the ROCm GDB has detected that this function is running GCN code and has disassembled GCN code. You can also see that this is not function main, this is function main ompfn0, as expected. So next, it's detected that it's not running on the device, that it is running on the device, that it's not running on host, and has chosen the else pass as we expected. This is single stepping the GPU code on the GPU. If I find out what's in the V variable, it should be the original value, which is 1. That's been passed in from the host to the device. If I do next again, and then check the value of V again, it is now set to 2 on the device, which is what it should be. Next, exits from the device and hits the next breakpoint. If I do info threads, you can see that the thread 3 has now vanished. And if I do print V again, you can see that the host side value of V is now 2 because the value has been passed back from the device. So, end of demo 1. Clear demo 2. So, demo 2 is very similar, but this time for OpenMP, and it's simplified so there's less to look at. We don't have the conditional. Let's not type out that long command again, let's just put it in. So it's demo 2 and the fopenacc is changed to fopenmp, but otherwise the same. Compile, start the debugger, switch to TUI. So there's our program. Let's set breakpoints on line 8 and line 12. Info breakpoints, it shows there they are set exactly as we would expect. So far the same as before. Run. We've stopped on thread 3 on the line that we would expect, and a backtrace shows exactly the same as before, slightly different message. That's just because of the numbers that GDB happens to find, but still one useful item on the backtrace. Info threads. We've got something new now. Where OpenACC just launched the one GPU thread, we now have several more. So we've got the 1 and 2 exactly as you expect, and 3 is the same again. It's on main OMP FN0, but we now have threads 4 and 5 on this GOMP simple barrier wait. And if I do more, there's more and more and more, and it goes up to 16. So we have what's happened here is that OpenMP always launches a whole team, and a team is, in this instance, has 16 threads. Only one of them is active. The other 15 threads are all waiting just to be asked to do something, which will never happen because there is nothing parallel in this example. So let's just check the value of V. It is 1. That was the value that was passed in. Next. Check it again. There we go. It's been set to 2 on the device. Next. And it's exited the thread. And if we do info threads, you can see that all of those threads have vanished. There's just the host threads left, and the host side value of V is now set to 2 as it should be. Next demo. This time a slightly more interesting OpenACC program. Still pretty noddy, but give it a go. Compile, run the debugger, switch to TUI. Okay, so here's our program. So we have an array of 10,000 integers which are uninitialized at the start. Normally in a C program that means that they'll be zeroed. And then we have an OpenACC parallel which copies them into the device at the beginning and back to the host at the end. And then we have an OpenACC loop which is set to distribute the loop across both gangs and workers. The loop just sets the data to the value of the iteration counter, so we should just end up with an array that is 0, 1, 2, 3, 4, 5 and so on to 9,999. Right, let's set our breakpoints on line 8 and line 11. So the entry to the device region and the first instruction back on the host. Run it, and it stops where you would expect. Info threads. Okay, so this time OpenACC has launched more than one thread, as you would hope. We've got gang 0, worker 0, gang 0, worker 1, gang 0, worker 2, up to gang 0, worker 5. On the next page goes as far as gang 0, worker 7, and then on to gang 1, worker 0, and at the bottom here we have gang 2, worker 0. And if we keep going through, there's quite a lot of them, so let's just go fast. So there are 3,336 workers in total, in 417 gangs numbered 0 to 416, and each gang has 8 workers, 0 to 7. So if we do 10,000 divided by 3336 and make it floating point, then we get there will be 2 or 3 iterations for each thread on this list to complete this array. So display I, there we go. So we are on thread 3, which is gang 0, worker 0, I guess that's the master thread, and that one got I equals 0, which is kind of what you would expect. Let's iterate to the next around the loop then. N. That's the next. Oh wait, what's happened here? We've hit a breakpoint again, and I is now 5,237 next again. Oh, it's gone crazy. 7709, and we've hit the breakpoint again. 8910, and there's the breakpoint again. My notifications have gone crazy. I do apologise. I'll shut this off. So we've got this problem. We keep hitting this breakpoint, and actually this is expected because the breakpoint is set without any conditionality for thread. It's going to get hit as many, 3,336 times. So we need to do something different. Now, if you are familiar with thread debugging on GDB, you may be familiar with the scheduler locking feature. And we could indeed set the scheduler locker on, and we could single step a thread, and the other threads would just sit and do nothing. But on the GPU we have a problem because we have hardware synchronization instructions, the barrier instructions. And what happens is that if the hardware hits one of those and the other threads are not running, it will just sit there and wait. And the knock-on effect of that is that our program hard locks up and our debugger locks up with it, and then we can't. And the only thing to do is to kill it from another terminal. So we're not going to do that. What I'm going to do instead is I'm going to start with a fresh run, so that we're back at I equals 0, and I'm going to disable breakpoint 1, so it's not there anymore. It's there, but it's not doing anything. So if I say info breakpoint now, you can see that enable n. on breakpoint 1. So now if I do next, we'll wait while the breakpoints run. There we go, I equals 8. Now you might have expected that I will be equal to 1 because it comes after 0, but what's happening here is that the workers in gang 0 are striding over this array. So we get n equals 0, n equals 8, n equals 16, and that's 3 iterations, so we should be done. And indeed we are. I equals 10,000 is the end of the loop. So next. Next. There we go. We have exited. So p data, print data. There we go. 0 to a lot. Incrementally. This is worked as expected. So quit. Yeah. The next demo is the same again, but this time for OpenMP, which has a few interesting variations. So this is the demo 4 file, and I've changed it to fopenmp, but otherwise the same compile line. So rockgdb a.out. Switch to 2e. Here's our program. Same idea, but this time we have OMP target pragma. It with a map. Map does the same as the copy on OpenACC, so this is copying data in at the beginning and out at the end. And we are going to create some teams which will distribute the loop iterations across the teams, and parallel for means also distribute them across the threads in the teams. So let's set breakpoint on line 8, which has actually gone to 10, and breakpoint on line 14 to catch the exit. Info breakpoint shows exactly what you expect, except now we have FN1, not 0. This is one of the differences with OpenMP debugging. So if I run this and do a backtrace, you can see that OMP FN1 has been called from GOMP parallel, which was in turn called from OMP FN0. This is because the .0 is where the code for the whole team is. There wasn't any team specific code outside the loop in this case, so the only thing it did was to launch all the workers. They're not workers, it's not OpenACC. To launch all the OpenMP teams, threads within the team. So the master one shows up on our backtrace here as FN1, and FN1 is where the thread specific code goes, which in this case is the contents of our loop. Info threads shows that we have a good number of threads, as you would expect. All of them stopped on this FN1 this time. So we have teams of 16 threads, lots of them. How many did we get? We got 120 teams of 16 threads, which makes 1,920 threads altogether. Let's just see what one of the slave threads is doing. So I'm going to switch to thread 4. So you can see here that this is team 0, thread 1. So this is the first slave thread. Let's have a look. Backtrace. So here we're running in .1 as expected, but this was called from GOMP thread start and GCN enter kernel. These are libgomp internal functions, which were called from the original team startup code. So these were sitting in a pool, just waiting to be told what to do. And when the master thread sent them a function pointer to call, that's what they did. So from the debugger point of view, you just need to be aware that these things are running in a slightly different way to what they do with OpenACC. You get a different backtrace, but there's not a really big deal. Let's go back to the master thread. And where were we at? We were looking at this iterations, weren't we? So display I shows that I equals 0. So the master thread has once again got 0, which is good. And 10,000 iterations divided by 1,920 threads means that each one will iterate 5 or 6 times. Mustn't forget, disable breakpoint 1, or we're going to get the same problem again. Next. There we go. Move to the next line. Now, I had this dummy thing, and you may be wondering what this dummy thing is about, and this is a workaround for a problem, which is probably not specific to GPU debugging, but just debugging in general, that the entire contents of this function has ended, fn.1 has ended up on a single source line. And when you do next, the debugger is going to keep going until you get to a different source line, and that's going to take a very long time if there isn't a next one. It's going to run through all the iterations of the loop and then exit the thing, because that's how the debug information is formed. So I put this dummy line in so that we have something to next over. That's all it's for. So next iteration, iteration 2, I equals 1. This one is not striding, you'll notice. This is good. This is just going to run through them one at a time. And there we go. We've run out of iterations. It was 6 like we thought it might be. We're into an internal function of loopcomp. No need to worry about that. Next again gets us we've exited. So we're done. This is the finish. We can check the data, and it's written it correctly and sent it back to the host as we would like. Right then, demo over. Thank you.
You are mute, Andrew. Okay.
Thank you. I was just saying thank you past me, and then I was talking to nobody but me, so that was good. I guess past me could hear. Right. Moving on then. So, as I was implementing the debug support in GCC, there was a number of issues that came up. I mean, obviously, we started out with just looking at the internals manual for all the dwarf-related hooks and macros and implement those. And that actually worked with an old version of RockGDB quite well. But then they updated their implementation to do things properly, and it stopped working. And it only ever been limited anyway. So if you were listening to Tony talk on Monday, you know that they did a bunch of work on dwarf extensions. We haven't had to use any of those yet, but there is some complications with the GPU. The first one I'd like to mention is that it has weird register sizes. It's a 64-bit architecture in the sense that address is a 64-bit, and it has a 64-bit instructions, and well, it has bigger than that in some cases. And it has, you know, the usual attributes that you might expect a 64-bit thing architecture to have, except that the registers only have 32 bits each. Now, it's not a problem for the instruction set because, you know, it can use pairs of registers just fine. But it was a problem for the dwarf representation. And we discovered that this is unique among all the architectures that GCC supports currently, and therefore had to go and retrofit a whole bunch of stuff in the dwarf generation code to allow us to use the dwarf expressions that have multiple, you know, for things that span multiple registers. The normal variables, it's absolutely fine. The GCC can cope with things that span registers. This is normal for larger types on many architectures. But for the specifically for the stack pointer and the frame pointer, there was a hard-coded built-in assumption that these things would fit in a register. So we had to go through and fix all that. And Dwarf itself kind of assumes the same thing. It does provide expressions to express that the register spanning, but all of the shortcut ways don't work. You have to use the full-on expression. So that was an interesting project. In the end, I ended up using C++ overloaded operators, so as not to have to edit too many places in the Dwarf code. The code mostly looks like it did, but it actually does magic things behind the scenes. The next one is the early debug information. So the offload supporting GCC, unlike other compilers that do offloading, is built on top of the LTO structure. So there's just one parsing step, and then it streams out the internal representation, and then the offload compiler streams that in and does what it wants with it. But it only gets a portion of the program code. It doesn't need all of the host program, only the offload bits. And normally when you do LTO, what happens is that the LTO objects contain some debug information pre-made. And then at the end of the LTO, when the compiler's generated actual assembly code and knows where everything is, it generates the rest of the debug, and then the two are put together by the linker. This also works for offloading, except for the fact that the early debug that comes with the LTO representation is in x86-64 format. We only support that so far. I mean, I guess it's in host format. And so we had to do some work in the Nook offload helper tool to rewrite this. So it does binary editing. It loads in the LTO object, extracts the ELF sections that have the debug code, creates a new ELF that has the correct ELF headers on it, and then goes through and converts all the relocation codes from x86-64 to AMD GCN, and then it weakens any references to symbols that may not exist, because the early debug code contains a bunch of stuff that's not relevant, and you end up with link errors, which is annoying. So we just weaken those, and that just makes the problem go away. So that was an interesting project. This one, I believe, is committed upstream already. Both of these two are. You don't need the dev branch for that. This one, though, you do. This one is in progress. So as I said, you only get the program code for the bits that actually get offloaded. The offload compiler isn't expected to offload the whole program again. And this ends up with an interesting problem where the debug information ends up nested inside a host program function, but doesn't exist on the target. There's no problem with this in terms of running the code. It's just a convenient organizational setup. But GDB said, well, this function doesn't exist, therefore any debug information I have for it is completely irrelevant, and just threw it all away, and we got nothing. So I had to fix this on the OG11 branch, and it has been submitted upstream for the main line, but it was rejected. It wasn't the correct fix, or Abid already decided it wasn't before he did it. Anyway, Abid is working on the proper solution for this, so we will get there soon. We will definitely be in GCC 12. And address spaces. This is one of the things that requires dwarf extensions that Tony presented. Last time I tried to implement this, I did actually come up with a patch that did it according to the specification, but GDB didn't support it, so I couldn't test it, so I haven't put it on the branch. Tony now tells me that the next major release of the ROCm of RockGDB will have support for this. No date for that yet, though. So I shall be getting back to this at some point in the future. But it needs address spaces because there are more than one memory. There's more than one memory on the device, and they all have, you know, addresses that start at 0 or whatever. But you need different instructions to access different memories. And well, GDB needs to know which one an address is in, or it's going to get something that is meaningless. This is only a problem for gang private variables right now. You know, you ask what the value of that is, and it says, I don't know. And then the next one is another of the extensions that are required is for getting pieces of vector registers. The GPU is interesting, in that it's different CPUs. In most CPUs that I've encountered, you get a full set, a complete set of instructions for scalars, and then you get a limited subset of stuff that you can do on vectors. And as long as you're inside that sort of stuff, which is mostly computational stuff, then you're fine. The GPU is the other way around. You get a full set of instructions for vector registers and a subset for scalar registers. So there are some operations that we can only do by putting the scalar in the bottom of a vector and setting the vector to a width of 1 and running the vector instruction. This happens quite a lot. Things get moved backwards and forwards between the register files. It's an interesting thing. But when you try and debug the program that's done this, GDB just, you know, you say, show me the value of V, and it says, and it gives you 64-bit wide vector because it's in a vector register. And then if you try and do debugger expressions with that, what you get is obviously nonsense. I mean, it doesn't work. So we need to implement some of the proposed extensions to make that work for ordinary scalars, and equally so for vector variables that are not 64 lanes wide. And in general, debugging vector code is hard, which is why I didn't do it anyway. If you notice, I set my demo to gang and worker, not to vector parallelism. So, questions? What do you think of questions? Shared notes are loading. We've already answered that on the chat already. I don't know whether you can attach to a running program. I had never tried it. I mean, I've been concentrating on trying to implement the debugger support, not the debugger itself. Tony did say something about it on the chat. Let me scroll back.
Yes, it does, Andrew.
Okay, it does. Okay, good. That'll be handy for next time it hangs up on me. I shall try that. You'll notice I also compiled everything with O0 because, as with anything, debugging optimized code is less well supported. You also notice that the compiler is set to still use OpenMP parallelism even at O0 because it's important to be able to debug these things in parallel. Even though that seems like it's an optimization, it is enabled at O0. Anything else? Any other questions? Okay, nothing about this one. Okay, well, I guess I'm just coming up to time anyway. So thank you, everybody. And I believe my slides should be available on the page shortly, if they're not already. And the video is not public on YouTube, but the URL is in the presentation.
Okay, thank you, Andrew. It was very cool. Okay, Jan, I put your slides in. Okay, where are you? There you are. I'm making you presenter. You want to test your audio?
Okay, can you hear me?
Yeah, very well. And I am disabling the video to save your phone data.
Yeah. I will disable video. I will just show for a short while. So I can be switching.
There you are. Okay. Thanks.
So then it looks perfect. Sorry, that's a pretty adventurous start. Okay, so it's my time to start with the talk.
Yeah, go on.
Okay, thank you very much. So I'm happy to be able to speak, even though it's virtual this time, and I hope I will be able to speak till the end of the talk, because the electricity got out here, and I'm not sure how long the data will stay. So that's why I disabled the video. So I would like to speak about the new IPA modref pass, which is something which we started with my student David Čepelík as a part of his master thesis. And then I continued working on it, also partly as funded by AMD. So I would like to start with a short review what kind of interprocedural optimizations we have in GCC. So the list is pretty long these days, but they are basically relatively easy optimizations. So the symbol visibility is the optimization which is mostly active with LTO, where we get the feedback from the linker in form of this plugin information, how the symbols are bound. And that means that we can bring some symbols which are externally visible internal, and that allows more optimization. Then you have the unreachable function and variable removal, which is the easy pass over the symbol table, and you take away everything which is not needed. And we have a profile propagation, which is trying to identify the cold pieces of the program and hot pieces of the program. Then Martin Eliška implemented ICF, which is an identical code folding pass, and that is merging functions which look identical in the GIMP level. We have the virtualization pass, which is something I was working a couple of years ago. We have the constant propagation, which is also doing a cloning, which means that we specialize functions for a given constant parameters. And we have construction destruction merging, which is something that was motivated by Firefox, because the modern C++ program has really thousands of constructors, which then touch a lot of pieces of the code segment. And we have inlining, which is the most active pass. We have some attribute discovery like pure cons, not row, non-free, no return, and malloc. And we do something which is called IPA reference, which is essentially a simple pass which collects lists of the static variables which are read and written by a function. And it's limited to the variables which are not having address taken, because otherwise the analysis is complicated. And we have a short pass which is merging contact groups in case it's possible. And finally, we have experimental points to analysis, which I believe there was a talk on it 2 days ago, which I unfortunately missed, but I hope to learn what was told there. I'm speaking from my vacation, so that's my vacation, other conference, to be honest. Okay, so this is the list of the optimizations, and if you ask, which of these optimizations are really important for the performance, then the answer is that it's basically the inlining. Most of the other optimizations are relatively, for example, spec neutral, which is sort of expected, but there are some exceptions, like the constant propagation is now very useful for some specific benchmarks. And also, if you look on the code size, then there are other very effective optimizations, which is ICF, the identical code folding, and the unreachable removal. So this situation is slightly disappointing from the point of view of LTO, because it means that we spent a lot of time making the LTO framework very general. But in the end, we really have a glorified intermodule inliner. So one of the motivations to work on the modref pass was to try to add another pass which would be effective. and which would catch some extra optimization opportunities on the normal code. Because the main issue is that since the compiler is so dependent on the inlining, tuning the inlining heuristics becomes a hell. So it's something which I do every now and then, that I'm trying to improve the inlining heuristics. And it is really very hard to balance the code size and the performance because as soon as you miss some important inline, the intra-procedural optimization simply gives up. What the modref is doing, as the name is suggesting, it is a pass which is looking for memory locations which are modified and referenced by the function. And the basic idea is that this information can improve the quality of alias analysis. In particular, it can tell if the given function call cares about the given memory location, and that in the end should enable other optimizations. How the pass is organized, there's basically a pass which is run 3 times. And at the compile time, which at least with the LTO optimization, this is the compile time, we do something which I call the local modref, which is done as the top-down propagation of the modref information during the early optimization passes. And this is quite important because during the early optimization, we do very limited inlining. So the functions we see are having a lot of external calls. And this allows us relatively cheaply to do a little bit more optimization around those calls. The second step which is done is that we get into the IPA mode. And the IPA modref is doing the analysis part, which means it's collecting the loads and stores in the function. And then it is streaming them into the object file, into a simple summary. I will show how these summaries looks like. And the second step is that at the VPA stage, which is the only stage which sees the full program, we stream the summaries in, and we do the inter-procedural optimization, which is actually kind of a simple data flow which runs over the strongly connected components of the call graph. And then we stream out the final result about behavior of the functions. And then at the link time, we basically repeat the same thing as the compile time. We are propagating the information down in the call graph, but at the same time, we stream in the global information from the VPA stage. This is done because after inlining, the functions become significantly simpler, and redoing the analysis is increasing the chance that we will get some extra optimizations done. So this is the basic outline of the modref, and it is pretty standard. All the other IPA passes are organized this way, and also the modref is relatively cheap pass. It is really not. It accounts something like 1% of the VPA time, and it accounts 0.0 something % of the LTrans and the compile time. So the basic test case where you can see what's going on is the following. Here I have a function foo, which is a function which is reading and writing global memory, and I'm forcing it to not be inlined because otherwise things will get optimized easily. And then I'm having a function test, which is writing the global memory and then returning it. But in meantime, it's calling the foo, and all the until the GCC 11, we was basically not able to optimize this code and conclude that the function returns 1 because we simply assume that the foo can do anything because it's not constant, it's not pure. So the code looks like this. There's this foo, which is not interesting, but in the test, there is this read from the memory, which is computing the return value. So what happens with modref is that this read, which I put there the arrow because I was not sure if I will be able to show something on the slides, and I'm still not sure. I can show. That's pretty cool. This is the optimizations which happens with modref, which is now enabled by default in GCC 11. And basically what happens internally is that the modref is computing the following summary. So if you look on the modref dump, the pass goes through every statement of the function foo, and it finds that there's a load of Q and load of P, and then there is the store on the pointer address, a load from the pointer address. And for each of them, it is recording the base alias set and then the reference alias set, which are the two alias sets which we associate with every memory access. You know, here they are the same, but if I made the example to contain a structure and access the field, then the base alias set would be the type of the structure, and the reference alias set would be the type of the field. And we made the summary, which looks like a tree, and the tree is organized in the 3 levels. So on the top level, we have the list of base alias sets which are accessed. So here it is alias set 1, which is probably the alias set of the pointer, and the alias set 2, which is the alias set of the short. And we have the list of the stores, so it is storing only short. So don't worry too much about the every access, but this is how the tree looks like, and it's easy to use it during the local optimization. You know, if you see the call to foo, and you want to test if the given value is modified or it is used by this function, all you need to do is to go through this tree and see if there is a conflicting aliases access, which doesn't happen here because the A is having type integer, but the pointers are pointing to short. So for this simple reason, you know, the propagation happens. So that was actually the original idea, which I started to discuss with David Čeperík for the modref. That's what we eventually implemented on the beginning of the project. But it turned out that you can do more with relatively little extra effort. You know, once the infrastructure is on the place, you know, you can save the summaries, load the summaries, and analyze the function. You know, you can pretty easily do more. So here is an example where the modref is able to track that the accesses are actually happening through the function parameters, which is, of course, the common case. You know, if you have C++ member functions, then you always have access through the disk pointer. So it is good to remember that certain memory accesses happens through the values which are passed to the functions by parameter. So here is again an example. You know, I'm hoping that the return value will be optimized because it is not accessed by or modified by the function foo. But at this time, you know, the alias sets will be in conflict because all of them will be of type short, but the array indexes are different. So for that, a little bit extra information needs to be tracked, and it looks as follows. So again, you know, with modref, this is optimized to return 1, and how the summary looks like is visible here. And basically, the main difference is that now this access, which previously was every access, is recording the information that the base pointer is parameter 0, and there is an offset from the parameter, which is 4 in bytes. There's a bit offset, and there's a size of the access, which is in bits, and the maximum size of the access. This is how internally the alias oracle represents the access ranges. So this is the same representation as in 3SSA alias. And now, you know, if the local optimizations go through the function test, you know, they are tracking the value which is accessed by pointer on the P on the index 2, and it can easily see that the store which happens in foo is not conflicting because it is storing to the different access range. So again, you know, this is mostly meant to help the C++ member functions because if you pass the object as a pointer, then it is very easily to track these access ranges, and it is making it easier to optimize around them. Because previously, basically, the main problem was that if you got some member function which was not inlined, the compiler got lost track about what's going on with the values on the object. So the code works only when everything gets inlined, and that's pushing the inlining limits up. So that's the second feature which the modref is having. And after that, and after end of David's project, I added another analyzer which is tracking something which is called the parameter flags. And the parameter flags is pre-existing infrastructure which was used to represent, for example, Fortran functions. We have something which is called attribute fnspec, and the attribute fnspec is having flags, and these flags are used by points to analysis. So in this case, this is another example which is optimized with modref and not optimized before. And actually, this is the only example which I noticed that the Clang is also optimizing. And basically, the idea is that here, again, before modref, we was not able to optimize the return value. After modref, we get the optimization done. And the basic idea is that there is a call to the foo, which is passing the address of P. And there is a call to the function, which is completely external to the unit. So GCC doesn't know what's going on. But if this EAF no escape is detected, GCC knows that passing P to the foo is not going to make the address of P to escape to some global memory. So that means that the GCC is able to track that after the call of the bar, the value is safe because it is an automatic variable, and the address didn't escape to any global memory. So that's the basic idea. We still have sort of missed optimization here, because if I remove this P equals to 2, then it would be still nice to optimize the return value to 1, because that's what the function foo does. But this is not what happens with modref. This is more job for IP constant propagation. And unfortunately, the constant propagation doesn't have any return functions. And this is a special case of the aggregate return function. So this is something which might be nice to have in future, but it's not implemented yet. And here it works in the way that there is a simple data flow analyzer which is trying to figure out what happens with every parameter. So here, we analyze the parameter P, and we infer the flux, which is direct, no escape, and no direct escape. And I will explain the other two flags in next slide. So this was about no escape. And the other flag, which I added the definition, so that means that the memory which is pointed to by the parameter doesn't escape to the global memory or other parameters. It can be still returned. It's a pretty funny definition, but it's what Richard told me it should be. And the other flag which I have added after looking into some test cases is no direct escape. Which means that you pass the pointer to function, and the pointer itself is not escaping. So here, the value of Q is still safe, but the value which is pointed to by Q is escaping into this global variable, which is again something that happens pretty commonly in C++, because if you think of this as being some simple class, then very commonly the class contains some pointer, and this pointer is stored somewhere into linked list or something else. But here, the important information which GCC is able to keep is that the Q itself is not escaping, only the value pointed by Q, and that means that this calling to the external function bar is not going to change the value. So, this is just some stupid example around to make the transformation happen. And again, this time I didn't do both versions, but again we optimized this to the return value. And I think I got the slide wrong, because this is the example from the previous slide. But then you have to believe me that it works. Sorry for that. Okay, so this is the direct escape. And in this case, that's the only flag which we can determine, because the escape and direct is not true here. And finally, there is this direct flag, which means that the value is used, but it's never used indirectly. That means that we never use the memory which is pointed to by some pointer saved on the location which the pointer itself points to. So in this case, the pointer is used, but it's only tested in the scalar computation. And that means that we can detect that the flag is direct. And as the consequence, we can figure out that storing this 1, 2, 3, 4 into the memory P is not necessary because the program cannot access it. So again, if you look how this is optimized, there is still this 1, 2, 3, 4, 1, 2, 3, 4 because it is being returned, but it is never stored into memory location. So that's the meaning of the direct flag. So that's all the main features. Yeah, finally there is a no clobber. I forgot about it. So that means that the parameter is read only for the points to analysis. So it means that the points to set, which was there before, the function call remains the valid after the function call. And here I have constructed a simple example where I have a P with the interesting point to set, either A or B. And then I'm modifying some C, which is definitely not pointed to by P. But in the meantime, there is this foo, which is doing something funny with P. And we need to propagate that this is not going to affect the value of this call. So that's the final flag. So this is what modref did in GCC 11. For the trunk, I have added 3 extra analyses. We start to track something which is called EAF not returned, which means that the value is not escaping to the return value. And we also have EF not read, which is kind of opposite of the no clobber. And finally, we have unused. So the last 2 things, they are not really that much useful in the real code. So I didn't bother to construct a test case. This not returned is doing better because we know that the values that cannot get into the return value. And that still adds something like another 12 or 15% of extra transformations on the top of the previous modref changes. So this is what the modref is doing. The propagation is actually quite straightforward. The modref is split between the local data flow, which happens at the analysis time, and the global data flow, which happens at the VPA time. And the local data flow is simply having a lattice, which is collecting something which I call the escape point, which is information that the flags from the function call are actually inferred to the flags from the parameter of the given function. Okay, so that's it, and I would like to say something about the benchmarks. So this is showing the number of disambiguations and the number of queries which GCC does when it is building CC1 plus with LTO. This is only the link time optimization. It doesn't account the compile stage because that's slightly harder to collect the statistics. And the first is with the modref enabled, then it is with modref disabled. And this is disabling modref, and it's also disabling the strict analysis, the strict aliasing. And finally, there's a disabling modref, strict aliasing, and PTA. And you can see that these numbers looks actually quite surprisingly good because the modref is increasing the number of disaggregations by 21%, and it somehow seems that it is doing more than the strict aliasing or PTA, which sounds somehow surprising given the complexity of the strict aliasing and the PTA implementation. But of course, the modref would not work without strict aliasing and PTA, so it is just piggybacking on the existing infrastructure. But it seems that it is really making quite a lot of difference. the complicated question is, how this difference is translating into the real performance. Because as you can see, the compiler is also doing significantly more queries. I tried to color code it, so the green values are the good ones. That means that the optimization happened or the subjugation happened. The red values are the ones which are bad, because the transformation, the subjugation didn't happen. And you can see that for some reason, the compiler is trying to do significantly more queries, which for another reason is being about the call statements. But in all, the number of the subjugations goes up. I will show you how this looks with the different oracles. So the previous slide was showing the disambiguations by type of the queries. So maybe I should say it. The first bar is the queries about 2 different memory accesses. The second one is about the memory access and a call, and the question is if the call is using the memory access. And the third one is about the call and memory location, and the question is if the call is clobbering the memory access. So I was hoping that the modref will actually help this call use and call clobber, which it does. But quite surprisingly, it is most effective about the memory accesses, which doesn't directly involve calls, but they depend on some global information being propagated. Okay, so this is how it looks with different Oracle implementations. So we do the type-based alias analysis, which is TBAA. We do the points to analysis, which is points PTA. It is split into 2 types of questions. Either we want the intersection of the sets or we want the subset relation. And then the rest is the rest of the oracles, which is basically the base plus offset analysis and the access path analysis. And as you can see, the modref makes the TBAA go up, which is because of the analysis I have shown in the first slide. It is something like 11% on CC1+. But the quite surprising thing is that the PTA goes up by 13 times on GCC. And I was quite surprised by this value, so I looked on other tests and collected statistics, and it really tends to help a lot to PTA. The reason is that the PTA is very sensitive on value escaping completely. If the value escapes, the PTA is up. So any help which prevents the value from being escaping helps significantly to the quality of the analysis. So I will get to the last slide because I think I'm running out of time. And this is how the performance looks like. So the modref is doing something like 0.5%, 2% on the spec in 2017 with O2, because my primary goal was to get the O2 better. It also helps with O3, actually slightly more, but I didn't put it on the slide. And this is how it compares to the other two tricks which we do. The strict aliasing counts somewhere between 1% and 1.5%, and the PTA counts somewhere between 0 and 2%. It counts significantly more with O3 because it enables more vectorization. And if any vectorization gets enabled, it actually gets up to something like 10% on the spec FP average. And this is all the things together. So this is comparing the base, which is disabling modref, strict aliasing, and PTA over the compilation that enables everything. So all in all, this is not a very big improvement, but it is actually not too bad. I wanted to show a little bit more, but because I cannot share the screen, I will not, but you can ask me later. And I will only show the slide when I collected some benchmarks. So essentially, this transformation or optimization is a hit or miss. It does nothing interesting until it disambiguates something which enables vectorization or something else important. There are a couple of benchmarks when it happens. Most importantly on Unbench and Polyhedron. There are also some regressions which we need to analyze. You cannot blame the better analysis to cause it, but it needs to be fixed. And that's all I wanted to say, and I'm happy that actually I was not disconnected, and hope next time it will be in person. And also hope you hear me.
Yeah, thank you, Jan.
Thank you.
So we have time for questions. Have like 1 minute, 2 minutes.
Okay. Yeah, there's a question on the chat. If this useful for if there are any plans to do with without LTO. Well, this pass also works without LTO. I didn't put the numbers on the slides because I wanted to actually show a bit from my browser. Yeah, it helps less without LTO, of course, because there is less of the context, but it is useful. With the code size, it is a slight increase in the code size on the average, which again is mostly about tuning the other optimizations.
Okay.
I will enable the video at least for a second. Okay, so thank you.
Well, thanks. I'm glad that your data connection was enough.
I must say this was really adventurous.
Now wait for the bill. Okay, thank you.
Okay, goodbye.
Ciao.
Thank you.
All right, so now we have a talk about this Core5, which is some sort of implementation of RISC-V, which is the coolest architecture ever made, or so they say, right? So this is who? Jeremy, is that you? I think so.
If you give the presenter to Enrico, it's going to be Enrico and Jessica.
Oh, okay, I see. Enrico, manifest yourself, and Jessica,
Enrico,
please manifest yourself too.
No. I think.
Hey, can you hear me? This is Enrico.
Yes. Yes.
Okay, I'm sharing my webcam. Give me a second, sorry.
Yeah, let me see if I can find your slides. No, I can't.
No,
yeah,
no.
Screen.
Can I share my screen?
Well, I don't think so, but I can give you presenter rights, so you can upload your slides. So
Okay.
Enrico, where are you? Let's see, there you are. So now I just made you presenter.
Okay.
So you should be able to go to this this blue plus button at the bottom left of the screen.
But I think now I can share the screen,
Oh, is that even possible?
Yeah.
Yeah, sure.
Okay, I didn't know that. Yeah,
Okay.
cool.
You can see? Okay, really cool. Okay, thanks, Jose.
Okay, thank you.
Okay, I think we can start, so.
Lovely.
Yeah, sure.
I've got a cough. Okay, so
Okay,
hi
yeah.
everyone. Oh, you ready? Okay.
Yeah,
Hi,
go ahead,
everyone.
Jessica.
So last year, my colleague Jeremy Bennett introduced our newly started project to develop GNU Toolchains for the Core5 processor family. So Core5 is a derivative of the RISC-V architecture with a number of custom instruction set extensions. So today, Enrico Tabanelli and I will provide an update on our progress over the past year. So where does Core5 come from? So our starting point is RISC-V, an open and extensible instruction set architecture that most of you will probably be familiar with. And then we have an early RISC-V research project, Pulp, that my colleague Enrico will tell you a little bit more about.
Okay, thanks, Jessica, for introducing me. I am Enrico Tabanelli, and I am a PhD from the University of Bologna. The PULP project started to explore new efficient architectures for ultra-low power processing. The main aim is to develop an open scalable hardware and software research and development platform with the goal to break the energy efficiency barrier within a power envelope of few milliwatts, as well as satisfying the computational demands of IoT application, which usually require flexible processing of data streams, usually generated by multiple sensors. Two important milestones of the project were RISC-V and Ariane. RISC-V is a 4-stage core that implements the RV32 IMC ISA. It has an optional 32-bit FPU supporting the F extension and includes ISA extensions for DSP operations such as order loops, SIM instructions, bit manipulation, and post-incrementing instructions. On the other side, we have Ariane. Ariane is a 6-stage single issue in order 64-bit CPU, which fully implements the IMC and D extensions. It implements 3 privilege levels to fully support a Unix-like operating system. To easily explore the design space for new chips, for example, the PULP project developed GDSOC, a full platform simulator supporting PULP architectures. Later in this presentation, I will introduce you the virtual platform more in depth and the work we did to enable testing GCC on GDSOC. Now Jessica will continue with the core family cores and which originated from the PULP platform. Okay, Jessica, you can go now.
Great, thanks Enrico. So finally, we have the Core5 family of 32 and 64-bit cores developed by the Open Hardware Group. So as Enrico mentioned, this is largely derived from the PULP project cores. So the Open Hardware Group is a global consortium of companies and universities, as well as other institutions dedicated to creating high-quality silicon IP and tools for deployment in commercial projects. So in our talk today, we'll discuss the toolchain being developed for the first 32-bit Core5 core CV32 E40P. So our plan is to support the 5 CV32 E40P instruction set extensions shown here. And to make it clear that we're targeting Core5, we'll use the vendor field of the target triplet. Thus, we have RISC-V 32 Core5 ELF instead of RISC-V 32 unknown ELF. And all Core5 instructions are prefixed by CV. We provide additional architecture specifications to specify either all 5 Core5 extension support by X-Core-V, or you can just select individual parts. For example, hardware loop would be X-Core-V hardware loop. So the current status of the project. At the moment, we've added support for all 5 of the instruction sets shown on the previous slide to the assembler and the linker. Work has also started in GCC, where we're adding built-ins and pattern matching for these instructions where it's appropriate. So earlier this year, GCC work was held up for a period of time until we had a suitable platform to test against. So I'd like to highlight 3 key activities over the past year that we'll discuss in further detail today. So the first is our approach to assembler testing, particularly how it may differ from that of RISC-V and other architectures. I'll also discuss how we tested using inline assembler for GCC. The second is how we overcame the blocker of having no existing target to test against. And lastly is the ongoing issue where we require a better mechanism for PSABI vendor-specific linking relocations. So starting with testing. So here's an example of just one test to illustrate what we mean by comprehensive testing. So this is an assembler test looking at the first argument in the hardware loop setup. In particular, we test the boundaries of operand and result values, as we anticipate this is where the majority of issues would occur. So for Core5, one thing we noticed was the relative weakness of RISC-V's target-specific testing. And for the assembler, we've added substantially to the existing tests. We took the preventative approach in recognizing where a problem may occur and writing tests in anticipation. However, these assembler tests will just check the syntax of the instructions, but we want to check that we've correctly understood the behavior of these instructions. So we're adding tests in GCC that use inline assembly to test the behavior of the assembler. So this is really important in ISAs like RISC-V, where we have custom extensions that are quite often not generated by the compiler. So we can't rely on the GCC regression test suite to find problems. So for example, in Core5, we have multiple instructions that can create a hardware loop. So at the moment, a hardware loop is only generated from memcopy and memset, and this only calls one type of instruction, CV setup I. So this one instruction sets up the start of the loop, the end of the loop, and the number of iterations. So we also have other instructions that set up a loop. So we have CV setup, which is the non-immediate version. We have CV start I, CV end I, CV count. So all these different instructions that set up different parts of the loop. But these aren't generated by the compiler. So if we hadn't tested these using inline assembly, then we could have easily missed some bugs. And so also you'll notice here that the compiler tests for Core5 haven't increased that much, and that's because it's still a work in progress. So now we're going to move on to test targets for Core5. So ideally, we'd like to test using physical silicon, the FPGA and ASIC implementations, but these are not yet available. So therefore, we'll use simulators in the meantime to verify our toolchain. So for performance tuning, we need strict cycle accuracy. And for this, we can use a verilator model of the hardware implementation. And the verilator model for Core5 is currently in development. So there are also some quick ways to create simulators. So the GNU Tools CGen is widely used to generate the assembler, disassembler, and simulator automatically from a scheme description of the ISA syntax and semantics. LLVM's table gen can be used in a similar fashion. So we use these for lots of RISC-V projects within Embecosm. However, we're not using this for Core5 as we have another solution that's even easier to adopt. So GVSOC is a simulator for pulp and pulp derivatives, such as Core5. So this is great for functional correctness and easy to use in continuous integration. So now I'll hand over to Enrico, who will discuss how we extended GVSOC to support Core5 and integrated it with the GCC regression testing framework.
Okay, thanks, Jessica. Okay, let's talk about GVSOC, the simulator. GVSOC is a powerful simulator for RISC-V-based platforms. It is a highly configurable and timing-accurate event-driven simulator that was born in the mainframe of the PULP project, just to allow developers to, for example, test new architecture functionality, for example, ISA extensions, and design new microarchitecture easily. For that purpose, GVSOC supports multi-cores and heterogeneous systems and enables simulating the full platform, modeling all the platform components, such as the core, memories, peripherals, and all the other components. The virtual platform enabled performance analysis based on a set of hardware counters and enables retrieving valuable debugging information to see how components interact between them. The system core is an instruction set architecture consisting of a base RISC-V ISA, which can be easily extended with new extensions. Lastly, the simulator was calibrated with hardware and currently has an timing accuracy in between 80 and 90%. Okay, after this brief introduction on the simulator, we're going to dig a bit into its structure. Okay, the simulator is divided into a static configuration and a hardware platform configuration. The static configuration consists of all the components, the IPs supported by the simulation engine, while the hardware platform configuration is the actual subset of IPs that we will use at runtime to run our code on the simulation engine. Okay, from the simulation, we get 100% accurate functional results. That is really cool, for example, for testing new microarchitectures, but also valuable timing and debug information. In particular, we can investigate the events that are taking place in each cycle in the pipeline, and for example, having a look at the content of the registers. Now let me show you an example of hardware platform configuration that we need to specify at runtime. In the slide, I reported a fragment of a JSON configuration script available in the open source GitHub link that I reported under the specified path. This is a configuration that enables simulating a full platform that is integrating CV32E40P core. Here we are instantiating, first of all the required IPs. So we are instantiating the core as such as CV32E40P, the L2 data memory, peripherals, and timers, and so on. As I previously said, GVSOC supports full platform simulation. For that purpose, it includes a runtime that supports a basic operating system. The runtime has been written in assembly to optimize it as much as possible, thus to leverage the power of the Core5 extensions. We integrated the extension into the runtime when possible. Okay, as you can see from the slide, I reported just a fragment of a routine from the runtime, post-SOC event store ISM, that is taking care of scheduling tasks. As you can see, there are both base RISC-V instructions, but also Core5 instructions that we added. Another important step in enabling simulating Core5 extension with the GVSOC simulator consists of integrating the the extension, so Core5 extension, into the instruction set simulator. In the slide, I reported the fragment of the Python script that implements the instruction set simulator. As you can see, there are both base RISC-V instructions, but also Core5 instructions that we added. It is necessary to add the binary encoding for each instruction, but also some metadata that, for example, in this case, are operands description. In order to support the previously added instructions, it is also necessary to implement a callback function for each new added instruction. When GVSock executes an application code and comes across an instruction, it will call it its callback, which simulates the instruction behavior and timing. Here, the reported callback takes care of the branch equal immediate instruction. From it, you can see that there are some special routines or special functions that are specific routines to support the performance counters. But more specially, there is a function ISS-perf account.
Enrico, you've lost your screen share.
Okay, sorry. I think I don't have the right now. I don't know why. I don't have. Okay, right now I have the button. Sorry. Okay, now you should see. Okay.
Yeah.
Okay, that's good. Okay, as I was saying, in this slide, I reported a callback function that the GVSock is calling when executing the code of an application comes across that specific instruction. In this case, is the branch equal immediate instruction. As you can see, there are some special some special functions that are used to support the performance counters, but more importantly, there is a special function, ISS-perf account taken branch, to evaluate if the branch is taken or not. And this is for the particular case of the branch instruction. But for each new added instruction, we need to add a callback that will be called by the GVSock. Okay, after that, the GVSock has been updated to support the Core5 extension, so we can run and simulate some code, for example, some application codes on our GVSock integrating the Core5 extensions. We need to move to GNU to enable running the GCC test suite on GVSock. Okay, here what we did was creating a new baseboard for the simulator. As you can see, we placed the GVSock launcher named GVSock Sim, and we included a precompiled runtime, libbasic runtime. And also we included a linker script. We also specified the stack size that our target platform is actually supporting. So in this case, 32 kilobyte, just to prevent executing tests with more stack usage. Okay, consequently, on the GVSock side, we need to create the GVSock launcher, so the GVSock Sim launcher. That is the script that the GNU will call at test time. Such script consists of 3 steps. First of all, we are going to generate the application image for the simulated flash. Then we are going to download the application image in the external simulated flash, and then we are going to run the application on the simulator. Okay, the application binary code is passed by the GNU, while in each of these steps, we need to specify the target platform that we want to run. And specifying, for example, here target equal CD32E40P, we are telling GVSock, the simulator, which IPs we want to use in our system. Okay, these are the results when running GCC test suite on GVSock. In that case, the Core5 GCC against the GVSock simulator. We achieved the result that I reported under the column Core5. I also reported the results when testing RISC-V GCC against the CGen simulator. Of course, you can see there is a mismatch in the total number of tests, since our Core5 GCC version is a little behind the RISC-V one. By the way, what turns up is that our toolchain has many more unexpected failures and unresolved test cases that we are going to address. Okay, digging more in depth in the unexpected failure test, we found out that the main issues were 2. First of all, on the simulator side, we find that many tests, of course, were deploying standard new lib functions, but the simulator originally supported a new lib custom implementation, including only a subset of these functions. Thus, we extended the GDSOC support to the standard new lib with the system call handling support, and all the new lib related tests passed. On the other side, sorry, we found that many old tests were not implementing the stack size check, since with the GNU you can specify a directive to say that if your target has not enough stack, you can skip that test. For that purpose, what we did, we added in those tests the GNU directive to skip the test if the test does not support the test stack size. Thus, all these tests became unsupported tests. We are planning to upstream these tests in which we added the GNU directives. Okay. By the way, we still have some unexpected errors. Many of them are related to the link optimization error, to the linked optimization. But we still need to figure out if the error source is our compiler, some missing the GNU directives in the test, or some kind of simulator-related issue. And so we are trying to figure out where is the error source. We also have failing tests with the optimization of trigonometric functions, but this could not be an issue for us, since generally, when doing some optimization, when using the optimization for trigonometric function, what is mathematically right is not always computational right, because on our target platform, we might have different roundings, data type bit length, and so this might not be an issue. Now I will hand over to Jessica, who will continue the presentation by talking about upstreaming issues that we are currently facing. So go ahead, Jessica.
Great, thanks, Enrico. So on to upstream our Core5 specific GCC toolchain. And there's a process that's well established for upstreaming vendor-specific versions of toolchains. For example, on this slide, we show the standard MIPS toolchain and 2 manufacturer versions. The same is true of other architectures such as Spark. So the GNU linker is not target specific, but supports all architectures simultaneously. For RISC-V, this means that all vendor variants are supported simultaneously. With multiple vendors and multiple custom extensions, this causes something of a challenge, but for which we believe there's a solution. So many RISC-V ISA extensions, including the extensions in Core5, use instructions that will need custom relocating in the linker. In our case, this occurs for the hardware loop and immediate branching extensions. So in 32-bit ELF, there are 256 possible relocations. For standard RISC-V, 59 are already in use, with 134 reserved for future standard use. So that's 64 relocations that are reserved for vendor-specific extensions. The challenge is that 64 relocations is not enough to allocate different ones to all the many RISC-V vendors. And in any case, this would require a central allocation authority that's able to ration a scarce resource. So at the moment, there are 3 solutions to the problem of RISC-V vendor relocation clashes under consideration. So first of all, switching to 64-bit ELF would immediately give us a 32-bit field for the relocation number. 4 billion relocations would surely be enough for everyone, but using 64-bit ELF is wasteful for a 32-bit architecture. So all RISC-V ELF files have an attribute section. The second approach is to use this to disambiguate overlapping relocations. The architecture string, for example, could enable specific subsets, providing control on a per file basis. However, if we have a core with multiple custom extensions, this could cause clashes where 2 different custom extensions wish to use the same custom relocation, but with different semantics. And in addition, per file basis is not particularly relevant. With LTO, everything becomes one huge file. So our final option is to use a second disambiguation relocation to indicate the vendor for the instruction, which would give control on a per instruction basis. So the advantage of this is that using a pair of relocations is already used in RISC-V to implement relaxation. So we already have an established infrastructure. So this last option seems to be the most flexible and easiest to adopt in RISC-V. So I'll look into detail about what we might need to implement this. So we'll need to extend the ELF table with one new standard relocation, RISC-V reloc ID, to identify which set of vendor relocations to use when interpreting a vendor-specific extension. The 32-bit relocation addend is used as an ID for the vendor. So I've also shown the first of the Core5 specific relocations, that's RISC-V CVPCRel URS1. Under this scheme, any instruction wishing to use this would also specify RISC-V reloc ID, with the Core5 ID to indicate the Core5 interpretations of the relocations 192 to 255 is what needs to be used. So if we have a look here, we can see Core5 and vendor A. On the first line of both snippets, we can see that they both have a different relocation, with sharing the relocation number 192. And then we have the instruction and its corresponding relocations. So looking at the second relocation of the two, RISC-V reloc ID, we see absolute plus some value. So it's this value that's unique to the vendor, and it's this magic number that we use to figure out which relocation to use. So this field is 32 bits long, so that means we have 4 billion IDs to use. Obviously, we still need a central authority to issue IDs, but as it's 32 bits now, it's not really a scarce resource anymore. So this could simply be administered through RISC-V International, solely needing to check for abuse. So I hope to work on the changes to the GNU linker to support this functionality later this year. So we'll be doing the work in close collaboration with the RISC-V International PSABI task group, which is led by Keto Cheng, who I think is actually here today, in order to ensure that we come up with a solution which works for the whole RISC-V community. So getting involved, and we strongly encourage you to get involved in the project as a developer, and we welcome your code pull requests against our code bases on GitHub. I'm the project lead for the GNU Tools project at the Open Hardware Group. So if you want to find out anything about the mailing list or any discussion forums, then please just drop me a message to the email on this slide. Okay, so this talk has been presented by Enrico and myself, but it's the work of a much larger team. And we look forward to answering any of your questions. So thanks for listening.
Hi, Jessica. It's Keto Chen. Could you hear me?
Hi, Keto.
Yeah, I think your proposal is kind of great for the relocation. In fact, I have similar solution come to my mind before, but I think it's still some part could be improved, since the vendor ID location is kind of an issue to me, since let's means we need a centralized place to location that. It's it's kind of problem. So I think it could be become a mixture with your proposal second and the proposal 3. I mean, the vendor ID could become a profile based string table. I mean, using the extension name as an index rather than a fixed vendor ID. And the mapping table we could install in a special section, and then I guess we could resolve the centralized location issue. Yeah.
Definitely.
Yeah. So personally, I'm open-minded for the accepting the vendor stuffs, and I guess we can have more discussion in next session. I mean the RISC-V BoF. Yeah. Really. Yeah.
I mean, I think we have to talk about this. Like pretty broadly, what we're doing right now is not working, right? Like we have the same thing at the whatever it is with the D1. Like something's got to change.
Yeah, agreed.
Yeah.
I think we do actually have some other questions.
Okay, thanks. We can maybe answer to some questions. Let me see.
So the first one I think is someone else. Oh no. The first one seems to be, do you plan to extend the GDB RISC-V simulator as well? At the moment, no, we don't have plans to extend that, but we do have obviously the Verilator model and GVSOC, so two different simulators that have, I suppose, two separate purposes.
Yeah, I think the plan for now is not to extend to the GDB RISC-V simulator. I know that there are some guys in Zurich that are also collaborating, that they have made a simulator for GDB, but it's only the core simulator. Okay, GBSOC simulator is supporting also the full platform simulation, so it's more useful also for other purposes.
But is it usable from GDB?
No.
Okay.
No. It's completely different. Okay. Okay, Jim Wilson. The GDB RISC-V sim still needs 20 pages streamed from.
That's not a question. I actually don't think.
Yeah.
Having a brief look, I don't think.
Okay.
There's actually any more questions for us. I think it just seems to be a bit of. There's a discussion going on there about. CJ.
Okay.
Yeah. That seems.
I don't see any other questions.
Okay. So thank you very much for the presentation.
Thank you, Jose.
And
Lovely.
for your work.
Thank
it's
you.
very nice. And now we have a coffee break. And let me see if I can do this super cool poll. Are you back from the break thingy? Yes, no. Start poll. Did that work?
Yes.
Yes. Okay, very good. Okay, so happy coffee, and then we are renovating at well, in 15 minutes. Thank you. Ciao. Jeremy, are you here?
I am.
Okay, so speaking of CGen, I think there are no less than 2 or 3 attempts for porting to Guile 2, and Guile 3. So I have a half-baked patch, that I was paying attention to, like on-off for the last couple of years. I think someone else, maybe from Embecosm, said that they had a complete port, because I think that's something.
Not a complete port to version 2. I think Andrew Burgess, who has been here but isn't at the moment, has been doing a little bit of work in his spare time. So might be worth just reaching with Andrew. Mary Bennett has on and off worked on it, but she's been much more interested in the CGen side of it rather than moving to Guile 3. Because that is a bit of a problem that we're on a.
I mean, now that Frank gave me the ability of approving patches, I want that merged, as soon as possible. Because,
well, why not? I mean,
sure.
I think it can take it forward now, and even if it's not fully complete, it makes.
Yeah, it doesn't matter. Yeah, I agree. So maybe if Andrew was right.
So I think Andrew's doing a bit of work, but I think so. Reach out to him. I say he's not on the call at the moment, but to reach out to him and ask him.
Yeah. Well, if you can ask him,
yeah, I will do. Yeah.
Yeah, if he can send the port to the list, then we can take it from there.
Yeah. But I don't think he'd finished. I think it was very much he'd started. So he may well just say, "Here's a branch with it partly done. Someone else can finish it off."
But there was someone else who did that too. It
wasn't. So in Embecosm, the people who've worked on CGen have been Maxim Blinov, Ed Jones and Mary Bennett and Andrew Burgess, but Maxim and Ed very much focused on delivering CGen models for customers rather than developing the infrastructure. And Mary's interest was less about the Guile version and more about what can you do to make, fix some of the issues that quite, Jim is pointing out. The CGen simulator, I think we've got support 64 different variants of RISC-V, but they're fixed and you have to choose which one you want. And 64 is only a tiny proportion of the thousands and thousands of different configurations you could have. So it would be nice to be able to, CGen was never conceived with the idea of something like RISC-V. How do you dynamically say I can create a simulator that runs with different extensions and I can at runtime choose which ones I want to support?
Okay. Well, I'm trying to get everyone to send all the, like private, half-made, CGen hacks to the mailing list so we can actually apply them. And something else I'm planning to do is to make a survey and to regenerate every CGen target in GNU Tools, all of them, and then see if we can decommission the ports and the targets, that are hopeless, basically, for which that they don't work anymore, if you regenerate, and maybe some of them, no one is using them anyway.
Yeah, I'm just sending an email to Andrew.
Okay, thanks. Are you moderating the afternoon, or?
So Gamathi is
okay,
moderating the next bit, but I'll be alongside, for any questions because it's the last session. So
right.
it's Gamathi's session. Yeah, well, thank you for your moderating.
Well, thanks to you for your moderating.
Oh, thank you, John. Mutually thanks, I think.
Okay, ciao.
Yeah.
Hi, Komati. I don't know if you got the poll when I transferred the presenter to you.
I did, and I responded back.
No, but I mean that. But is the poll still on? I mean, did it survive the change of ownership?
I don't see a way for me to do that. Let me see.
Below notes.
No, it disappeared.
Okay, I see. Well. We will have to do without the poll.
I guess so. If the speakers of the next session, if you guys are on, if you can turn on your camera, letting us know that you're here, that would be helpful.
I actually have to run for a second. I'll be back in a minute or two. Sorry.
Okay, sounds good. Hi, Jim.
Hello.
Should we get started? Do we have, or should we wait for Palmer to come back?
I think Palmer was planning to lead the session, so we probably ought to wait for him to return.
Okay. All right, so welcome everyone. I will be moderating the second half of today's sessions. Welcome to the RISC-V BoF. Jim, Guido, I will capture questions on the shared notes from the chat, so you can directly look at the shared notes. And off to you guys.
How can I share my screen? I don't see some button. Can you share? Oh, okay. I see. And here is some quick slide for today's some topic we would like to discuss. And I think Palmer is back. Okay, so there is only few topics I would like to discuss. First is the vendor extension policy. I think some issue already raised by the last session. I mean, by the Core5 talks. So I think that is kind of long time issue in the RISC-V. RISC-V is an open ISI which allow vendor to extend your extension. But for a long time, we are not accept the vendor extension on the upstream tool chains. So I think it's good time to discuss what the accepted criteria for the upstream vendor extension. And the second topic would be is the iFunc for the RISC-V is kind of to me, I think it's an emergency issue need to resolve soon. And the last one is the open discussion. And the first one is the vendor extension policy. I this only few issues there. I think we may need to discuss. First is what is the accepted criteria. I only list a few things I think should be the list. For the first, I think it must be the open spec. What mean it must have you can found the instruction encoding in the semantic on the public access, and I think it must have some open source simulator so that we could have some way to verify that it actually work. For example, the Spike or QEMU or GNU simulator either is fine. Yeah. And I think and the next one is it must have an extension name and a version so that we can have some unified way to control that, like the standard extension. we could control it via the NRG options. Yeah. So for this issue, does here any comment or question about it? Or Palmer, how do you think about that?
Sorry, I was getting yelled at by work folks.
Okay.
That's the problem with these virtual conferences, is that the computers are still there, man.
Yeah.
Anyway, yeah, I mean, like, we kind of talked about this a bunch of times, and like, okay, so obviously what we're doing now with keeping all this stuff out of trunk is not working, right? Like it's just leading to even worse fragmentation. The goal of sticking to right, like sticking to the standard stuff was to try to avoid this kind of fragmentation, right? That was the goal, to get folks to work inside the RISC-V Foundation, not do custom stuff, you know, or at least not do custom stuff that's like, you know, when it's possible to align it and whatnot, right? But yeah, okay, that didn't happen, right? And we kind of have to accept that reality, right? And you know, like if there are chips with custom extensions, and there's no way around that, hardware doesn't go away once it gets created. So either we like force everybody to work out a tree and effectively go fork the whole software stack, or we start accepting their code. And I don't want to force people to fork. So I don't like. We are opening a huge can of worms by doing this. I don't know exactly what the rules. Hey, Jeremy.
So I was going to add a comment from that, which is, I think if you look at some of the groups working who would be nice vendor extensions, you can look at Open Hardware Group, you could look at Low Risk, you could look at chips. And I think you start saying those are the groups that are funded because they're tending to be doing commercial chips. And they're probably the people who are therefore going to have the resource that can be deployed. So it's not just, hey, you're getting forking, you're probably locking out. Whenever you do a vendor specific, most of your work's actually going to be contributed from fixing things in the core stuff. So I think we're losing access to a lot of core contribution.
And that's my problem with fork, right? Because like, okay, if we tell people fork the software stack, ship your stuff, right? You know, like we lose that, like that willingness to contribute your fixes back, right? And that's like my worry there. I totally agree with you.
And,
you know,
and the nice thing is, GNU's GCC solved this problem years ago. I mean, we had the example in the previous talk of the MIPS. You've got the standard MIPS, you've got the MTI MIPS, and you've got the imagination MIPS. And that's what the point of the vendor field. And I think so long as you have a degree of criteria about common sense, and RISC-V, of course, is unique. It's taken the policy in the way far beyond the original idea. And there may be some criteria you say for acceptance, but broadly, I think you don't want to make those any much harder than the standard GCC hurdles. The standard for acceptance in GCC is pretty high anyway. So
yeah, I mean, I agree. This is a discussion we've had many times. At least I don't know how much of it's in public, but certainly in private we had it a bunch of times. And you know, like I personally don't see a reason why RISC-V should have more stringent acceptance policies than like the broader community acceptance policies, which generally revolve around, you know, like, is there hardware and are people actually using this, as opposed to, you know, does it align to the kind of standards body, right? That opens up a huge can of worms. I get that, but you know, there's a reason everyone else does it that way. It's because if you don't, like, you're just going to get forked software stacks.
And maybe to jump in on the same topic, we're having the same problem with the non-standard, which now becomes vendor-specific vector extension. And we've already agreed on, or we're reaching an agreement there on how that can become a vendor extension, and how the vendor who pushes it in will also have the maintenance burden. So I fully agree with Jeremy here. So if we pull things in, it allows us to actually leverage the resources and bring more people closer to the tools instead of having fragmentation and branches.
Yeah. Okay. Well, I don't know, Jim, Keto. Any thoughts?
Yeah, I think the vector stuff, I mean, the T-head, their vector 0.91 is kind of a big mess, since it's really incompatible with the current vector stuff, especially in future we will have the vector intrinsic. I believe it's totally incompatible.
Yeah.
Yeah. Otherwise, for the BUTO part, I mean the OP core assembler path, assemble, disassemble, I think it's already easy to support multiple version, which Nelson already put a lot of effort to support that. So I believe supporting that on BUTO side is relatively easy and workable now. But yeah.
My problem with that is that if we only do the easy things, we don't get to benefit from the people doing the hard things. It's like right. It's like turning people away who are willing to contribute because like we don't have the time to accept their contributions. It's just like it's not a sustainable way to manage things, right? Like we have to grow the community. If we don't accept people's code, they're going to go somewhere else.
Yeah.
Right. That somewhere else may be, CISC-V or whatever it ends up being called, but that's bad. Right? It's still bad.
And you may that probably touched on a point about actually bringing more people into the community, so you've got more reviewers, and I think it's a virtuous cycle. You make it easy to contribute your stuff. More people contribute. You start to get more reviewers available.
And sorry, but look at where we are with the vector stuff right now, where we're kind of stuck to doing assembler and intrinsics and stuff because we don't have the broad GCC wide changes that are necessary to handle this new programming paradigm. Like that is the same between the T-head and the standard, right? So we can benefit from a lot of shared work there, and that's really genuinely difficult stuff, right? We're not going to be able to do that without like serious resources.
There's some interesting comments I see in the discussion about whether you use a vendor field or a -m extension from Joseph and Pedro and Tomish.
So I personally think that there is no technical reason why we cannot keep these all available in the same toolchain, right? If vendors, if people want to ship toolchains with the vendor field set and they want to change defaults or drop stuff or whatever, happy to help folks out. But having everything in one toolchain is super useful from a just kind of sanity perspective, right? I don't have to go scare up specific toolchains to compile various types of code and whatnot. It is a bit of work, but I don't think it's a ton of work.
So one of the things that you might consider is that people might want to do fat binaries, and then having a single toolchain would be quite nice, and also having the relocation support for all of the vendor extensions in the same toolchain so that they can just recompile and put it all together.
Yeah, that's why I've been pushing really hard for the relocation support to allow extensions from multiple vendors in the same binary, because I think punting on that is a very short-term focused decision that will bite us in the long run, because there are vendor extensions. They will not be the same between different chips. Those chips are shipping. They're in real hardware. There's going to be real software stacks that run on those, and we will need to deal with detecting those at runtime and running the correct code on them. And if we provide people no way to do that inside the standard, we're going to end up with a huge mess of forked user space, which will be very bad. Very bad.
Which I think is, if you take the approach that Jessica outlined, that does give you that, because you actually effectively are nominating each vendor with each relocation. That's and the customer.
Yeah, I think. Yeah, many of us have proposed similar things there. So not.
Oh yeah, I know it's not a unique thing. It's building on what people. I'm sorry, I wasn't trying to claim that was a unique contribution.
Yeah, I guess I think the exact I actually think we need to go even farther than that, and that the exact mechanism should allow like decoupling the vendor from the vendor extension, because I think vendors will start to implement each other's extensions. But we've talked about that somewhere, so I'm not, not dead set on that one. Right?
Well, with
This
the
is
case of,
you
go ahead, Kito. So in the case of Vector 07, we will have exactly that. So multiple people have implemented that, and we'll make it an XT head now, and somebody else may have or may refer back to that one, even though it's an X string computing, for example.
Yeah, exactly. So I think like I would like to give like us to have a vendor namespace, and then the vendors to have another namespace for extensions that they can do with what they want, and then that to have relocation types. But again, not really dead set on that one. So, and it is like the bit packing does get uglier. So, this is probably a better discussion to have on like a mailing list or something, because it's very hard to discuss.
Possibly also we ought to perhaps focus on getting someone to actually submit a starting candidate, say, here's a patch that implements this, because actually what we're lacking is anyone actually having submitted a patch that implements any scheme. At least if someone implements a patch, then you have the opportunity of saying, here is a better patch.
Yeah, I guess we have to at some point stop sitting around and talking and actually do something, right? So, but anyway, I'm going to try not to sign up.
Well, I'm hoping that one of my team will be able to, because I don't think it's been talked about enough that the problem is well understood, and that makes it implement. So I'm hoping one of my team I can make time for them to actually contribute that in the next few months.
Awesome, yeah, that'd be great.
Okay, so just go to the second issue. The branch, I think also people should hope this could be in the trunk or master branch instead of the integration or vendor branch there.
Yeah, I mean, I think we need a path to getting these on trunk in order for this to work, right?
Yeah.
Like integration branches are cool and all, but if that is the end point of this, then it kind of doesn't really count. So.
Yeah, since maintain the safer of the integration branch is kind of miss. Yeah, it's need to maintain by our maintainer, just like Nelson has regular repair states.
Yes, Joseph brings up obsoleting things. So whenever somebody brings up obsoleting things, I tell people that I would like to first get to the point where we have enough shipping hardware that we have things we don't care about. But yeah, no, I totally buy it. It's going to be a mess. And that's part of the reason why we're pushing back so hard on taking this stuff, is because like, how do we deal with some vendors' custom extension in like a decade when that only exists as some, very non-standard software stack, low volume part that nobody can, find a power supply for anymore. Yeah, Philip, I thought we all agreed to move away from the GitHub branches.
Yeah.
Can we just like put it in archive and put a big message up that says don't commit stuff here or something? Like
the PLC
I agree.
are still using GitHub, so that might be tricky because they're students, interns.
Yeah. Okay. Students can speak SMTP. But anyway, I don't know. Sorry.
but I know the Jun Wilson's point. I since like the PLC, the folks prefer working on the GitHub rather than upstream.
I get it, but I think it's one of those things where, like, if we continue to use non-standard development methodologies for the RISC-V bits of stuff, we're never really going to get people into the community, and we're always going to have this problem of RISC-V being this thing off to the side that doesn't really play ball. Right? We have to get out of that methodology, especially as we start doing stuff like the vector thing. We're going to need like actual serious work in GCC. I mean, like, I don't want to trivialize what we've done, but serious, like, optimization passes and whatnot that will have effects on, the generic GCC code as opposed to just staying in our backend.
Okay. So, okay, the last topic I think we could discuss offline, I mean the vendor relocation, since Jessica Mio has proposed some proposal there, and they have proof of concept. So I think it would be better to have some discussion later.
Yeah, I think Jeremy's right here. Let's have somebody send a patch and then talk about it, because I think we've talked enough without code.
Yeah. And personally, I would like to kind of become let's standardized to the PSA. Yeah, especially I know you definitely want a relocation entry for that. Yeah. So either I think GitHub issue for the PSA via and patch set for everybody would be great. Yeah.
Cool, great. Hopefully someone will sign up to do that.
Yeah, cool. Yeah. And so I think that's all about the vendor extension stuffs. And I think the second issue is kind of become very serious soon, since I think for the RISC-V is got some problem here. Since we have the Huawei cap to pass the Huawei capability to represent which extension is there, but it's run out soon. I mean, there is only 32-bit if we consider RV32, but the RISC-V have a bunch of extensions there in near future. I don't even remember how many extensions we will have in next year. But
more than 32, like many more than 32. Is the key point there.
Yeah. So I guess we really need a new mechanism to detect the feature now, and what we need, what kind of info we need. First, I think it must easy to pass by resolver function if possible. Yeah. Otherwise, it's would be hard to use. And the second goal I want to make is I want to make sure the vendor extension could be detected too. Otherwise, yeah, this page we just discussed a lot of vendor stuff. If that can detect, okay, I think it's less use. And I hope there should have some extension name and the version info, although currently version info didn't provide too much extra information. For example, the F extension from 2.0 to 2.2 has no obviously change from to the software side, but I think there is info in case we may need that, so it must encode we could access that. And for the vector stuff, we may need a vector length, but I think it don't need to provided by the Huawei cap, since it could have some CSR, you could just get that. And the cache info, I think the basically the generic infrastructure already provided that. We just leverage that, it could be fine. And here's some other info we are missing. We need to handle that. And a few more background why I discussed that, since Palmer is there too. Yeah, since he's important kernel developer. So this I believe must coordinate between the tool chain, especially the GNU and the kernels to come out interface there. Yeah.
Yeah, the cache info stuff is broken. We need to scrap that sooner rather than later. That was a mistake.
Yeah.
I think we talked about this. I also think we need to figure out some way to plumb the microarchitecture through, because iFunks are going to want to switch on that, especially for these more complicated extensions like the vector extension.
Yeah. And okay. I just go very quick. There is some proposed come to my mind before, and since I have already discussed this issue with many people, so here is some thought or proposal I heard before. Just quick go through. The first one is the most important thing is we must just treat the heavy cable to as a pointer. Otherwise, just extra little bit doesn't help anything. Yeah. And how could we use that? First, maybe point to a raw ISA string or a preprocessed ISA string like linked list here, so that we could just traverse that to check which extension is a variable, or a bit vector scheme with variable length encoding. But I guess it will introduce some problems. We must have some centralized way to encoding that, especially that would be very not friendly for the bender extension. Yeah, I believe. Or the currently RISC-V Foundation have some proposal about the configuration structure. It's using some DR or PR encoding, but to me, I think it's too hard to pass in.
I agree. Let's not couple ourselves to that one because that's something that's been made up.
Yeah, it's even need a very complicated C parser, and you must know the structure.
Yeah,
it's meant to be a low-level configuration tool. So the higher up the levels, the more the assumption goes that this has been pre-processed and is being used differently already.
Yeah.
Anyway, okay. So, or any printer of one of both or Mistral or other proposal? I don't know. Jun, do you have any preference or comment on that?
I haven't been looking at this problem specifically, so no, I don't have any suggestions. Just
okay.
Find something that works.
Okay.
Yeah, I think, I don't know. We just need to pick something and go with it. It doesn't really matter. We just need to figure out how to jam all this stuff in there. And whatever it is, like it needs to be one of these extensible in memory things. Because trying to cram it all into these fixed size structures is not going to fly.
Yeah.
For the vector extension, we may also need additional info like the minimum element size and whether or not it has FP and the vector register lengths and stuff like that.
Yeah, it's kind of my worry. I'm like also, and maybe this is like too much to worry about, but I'm worried about the vector unit ending up with like a non-smooth performance curve where if you turn on the vector unit but don't use it that much, you end up harming performance, right? So you may not always want to turn on the vector unit for ifuncs if it is available, which means that we don't really have this static concept, right? Now, I don't know if that's just something we should just not fix because that's hard, right? But like I am genuinely worried about like, I don't know, like a glibc mem copy routine firing up the vector unit and then sticking us with 64K of state save on all these context switches when we're not really benefiting from it, if that makes any sense.
Mm-hmm. Yeah, okay.
Right, because if you think about it, like we're going to turn the vector unit on for basically every process because we're going to detect it and we're going to, we're going to need to fire it up, doing basically anything in the dynamic function resolver and all that sort of stuff, right? So worry about ending up in. Sorry.
On the other hand, Palmer, do you envision that this is one piece of information that's passed to every process, or would the loader enable the vector information in the state or inject it in the auxiliary vector only for some and not for others, depending on what the hints in the binary are?
Yeah, I mean, I don't really know what the right answer is here, right? I kind of have puzzled over this a handful of times. Certainly one option is, to whack something in the ELF that says like, I am going to actively use the vector extension and then handle it slightly differently. I guess maybe the broader worry is like, whether or not these static things are the right approach, right? But then we stop playing nice with ifuncs at all. So I don't know if we're just adding too much complexity to the problem.
Well,
anyway,
if you want real complexity, you can start thinking the way that some of the CMO discussions are going. What happens if the process gets migrated to a core that has different capabilities?
Yeah, that's a that is another can of worms that we have to look into. And I think okay, so you know, one option is for HWCAP to just kind of expose the set of capabilities that the hardware has, which is a static thing, and that is at least a simple and understandable interface to provide to user space, right? We can argue about whether that's, and this is the problem with the cache thing, right? Whether we have like the, you know, the entire system in there, or we have just the core you're running on, or but anyway, you know, at least that is a static thing, unless you talk about VM migration, which, you know, we really don't have any mechanisms to deal with right now. So yeah, you know, we can do that, and then we can have yeah, Joseph points out Intel's doing the same thing, and that's why what makes me worry about it, because we're just kind of creating the same problems that everyone else is trying to deal with. I don't know if there's a solution to that one, but I saw a lot of arguing. So anyway, sorry, I'm super tired.
Yeah.
Yeah,
but regarding this ifunc selection or policy for detecting the correct function, I think it's not completely independent of the vendor or of the processor which we are running on. So we also need to consider this information.
Yeah, I think we talked about that a little more explicitly at the other session, but definitely it would be short-sighted to rely on all vendors having like the same performance code for the same ISA, right? Maybe for the like slightly simpler stuff like bitmanip, you can rely on vendors who have it going reasonably fast. But for the vector unit, you're definitely going to want different string routines for different microarchitectures. Like there's way too much available implementation space to rely on vendors all having the same performance trade-offs. So that needs to be part of this proposal.
Mm-hmm. Yeah. Okay, and just mention we mean have two slots could be used. It's the AT platform and the AT base platform. It's defined by some architecture, but not used for the RISC-V. Just mention we could have two more slots for that to put some more information. Yeah. Okay. So anyway, I think this still needs some long discussion, and just Philip has mentioned in the chat, it's not soon, it's just now. So I guess we should have some discussion after the BoF, I mean offline. Yeah. And to continue to complete the proposal.
I think for this one, we're also at a point where like just need to come up with a concrete proposal and have at it and then argue about it. So
yeah, okay. And so just I think our time should almost run out. So does here any topic you want to discuss or ask here?
Well, we could mention that there's a whole bunch of new extensions that just went into public review. About 15 of them.
Some of them are frozen.
Most of them deal with machine mode and supervisor mode, but the vector extension finally went into public review. That's the interesting one.
And it is frozen, and hot, like it's frozen. We can actually do stuff with it now. It's great.
Yeah, but I think that luckily we don't need to care about the all supervisor stuffs in the
No,
iFunction.
you don't need to care about the supervisor stuff, but yeah, anyway.
Yeah, user space don't need to care, but I know you need to care.
Yeah, I have many problems, but yeah. Anyway, no, I think for this BoF we can focus mostly on vector. I don't remember if minip is frozen, but yeah.
Yeah, since I think the
bit minip A, B, C, and S are frozen, and
Okay,
also the
great.
crypto. Some subset of the crypto has gone into public review.
Yeah, I'm less worried about that because I have a feeling that that's not going to be something we can generate code for like ever. So yeah, that's likely to stay in the assembler. But anyway.
Well, there's going to be some built-ins most likely, and the kernel is likely to want to have some assembly libraries in there.
Yeah, yeah. But I think like the vector stuff is going to require like big codegen in GCC. So that's kind of like the top,
yeah, auto-vectorization
right?
for the auto-vectorization is going to be fun. I mean, just look at the amount of resources and lines of code that ARM put on SV.
Yep, and we're different, different enough. So yeah.
We have a prototype GCC patch, but it hasn't been actively worked on for the last year and a half.
So you guys planning? Sorry.
Most of the V work is happening in Clang, and Clang does have usable vector support.
Are you guys planning on like resurrecting the V stuff?
Alibaba has actually been contributing to it, so they might be interested in helping improve it.
Maybe we can start a thread to figure out how to get that rolling again, because I don't want to lose it.
So I think that's all, and I guess our time slot is end, or we will have more time. I'm not sure.
You have a few minutes.
Oh, okay. Oh, we have extra.
Yeah.
Yeah, okay.
Go until up to 15, quarter past the hour.
Okay. So, okay, does here any topic or question? And okay. Since like no, so I guess we can end this VOF, and I believe some discussion we could have continue that in the offline, especially for the iFunk and some vendor relocation stuffs. We could have more some code to have more practical discussion there. So
Jose, you're talking.
right?
Sorry, you're asking. Jose asked about simulate. You're talking about like the CGen version or what's there now.
Yeah,
I'm sorry to be a pest with this, but
it needs to be fixed because having something that's kind of I don't know halfway done and old is not really the way to do it.
Well, Embicosm has a CGen simulator port, which is really cool, except it has a serious problem that it only supports a small set of architectures. So instead of supporting all the thousands of different architecture variations, it only supports about 6 of them. And I don't know if that can be fixed.
So Jim, these days it supports considerably more than 6, but it's a finite number, and it is a small proportion of the set that you can handle. And for individual customers, it works fine. And it's to meet a specific customer requirement, which is a 24-hour turnaround from specifying a new instruction to be able to try it out in the simulator and the zipline assembler. And that led to us. So we've got all the major extensions and what was the B extension, except of course that's now fragmented. And it does stretch CGen as it is today to its limit. But the problem is you've got to know at the start exactly what you want. You haven't got what you've got in your simulator, which is the dynamic ability to choose which extensions you're going to run. You run CGen, you generate a simulator for this combination. And if that's not the one you want, you've got to run CGen again. So I accept that that's the limitation of it.
So Jeremy, is it possible to generate something that supports all of the extensions and have stubs that check like an MISA type thing and kick out? Does that make sense?
Yes, it does. And yes, it is. And I think we do some of that stuff.
Yeah.
But it's
because I think in the long term, we kind of want to move our simulators towards that, because we are approaching the point where software is going to start to turn on and off extensions dynamically. So like if we got to bite that bullet, maybe that will fix this problem, if that makes any sense.
Yeah, so I think this is where having Jose as maintainer of CGen, we've got someone who actually has a concern.
No. Hang on a minute.
I tried to get away with it, Jose.
But right now, what is in opcodes for RISC-V?
There is I'm not. So there was a pull request from Andrew for a spec for the what I think amounts to the G extension, but I'm not sure where it is.
But is the current opcodes for RISC-V in upstream based on CGen as well, or not?
No, it's handwritten assembler.
So does it make sense to have a CGen-based simulator and not a opcodes CGen-based?
Like the current sim port is crusty, so I think it is sensible to replace that, even if we do not also replace the assembler.
Right. Okay. Well.
And that is what we do on some out of tree work, which is because the thing is the assembler is now well established. And it's dangerous to replace something that's well established and trusted with something, however wonderful, is still new, because you potentially introduce new bugs. So it's perfectly possible to turn off the assembler generation and just generate the simulator.
And if there was some way to also generate the assembler and hide it behind a, do RISC-V CGen assembler or something flag, it would be fine. It's just that, like Jeremy said, assemblers are the sort of thing that that you really don't want to break, and they're somewhat complex.
Yeah.
I'm kind of worried that there would really be no path to getting a critical mass behind a CGen-based RISC-V assembler unless it could be somehow coexist.
Well, I like handwritten assemblers more myself, so.
Yeah, CGen is a tool for a particular job. It's very good as far as it goes, but it only goes so far. You could mask the assembler behind things, so you really had two assemblers, and you could actively switch in the CGen one if that's what you want. But it's one more piece of work to be done.
Yeah, I guess another option is to have it generate something that fits the instruction tables that we have, which are somewhat regular and may allow new extensions to go in, generating the tables while keeping the existing assembler, if that makes sense.
That's a possibility, because that's all it is a table generator. So potentially you could have a version of CGen that generated the tables we currently have.
Yeah, and then you could imagine modularly moving things over, or at least putting new extensions in, or something kind of sane and maintainable. But again, it's not like I'm dead set on changing the assembler. It works, so why mess with it?
Okay, does here any topic would like to discuss? Okay. So if no, I think that's all. Thanks everyone.
All right. Thank you, Jim, Kido, and Palmer.
I just wanted to point out we have another BoF tomorrow. More on the kernel side, but
okay,
we'll be talking more. maybe not Kido's problem, but definitely mine.
Yeah. Okay. Goodbye.
All right. Thank you, everyone. So we have the next session. Aaron, are you on the call? Okay, I see you.
Yes, I'm here.
All right. So the next session is a BoF for the register pressure sensitivity in the GCC middle end. After you, Aaron.
Okay. Do I? All right. Can you load the slides that I've uploaded?
Unless you sent them directly to me, I don't have access to your slides. So you'll either need to upload them yourself or screen share. So there should be a little blue cross in the corner, blue circle with a cross in the bottom left corner, and that'll allow you to either upload them or share your screen.
All right, that looks hopeful. So should I just go ahead and go then? On time? Are we waiting for anybody?
Nope, feel free.
All right, so this is an issue that I first encountered about 5 years ago or so when I messed around with trying to implement pressure sensitive inlining, and at the time I suppose I could switch to the later slide. That this has all the different issues, but what I discovered at the time is there's really, I mean, there's obviously, for good reason, there's no concept of what is the register pressure in the middle end, but there are a bunch of things which we might want to do in the middle of the compiler, which it would be good to have some kind of analog to this to guide us in terms of not doing stupid things. Now, at the time, people said, "Oh, the new register allocator will magically fix all of this, and there won't be any problems." But that isn't the case. So I think you still need to pay attention to these things and not overwhelm the register allocator. So I've listed a few things here. Inlining, obviously, you don't want to necessarily dump one inline a function that's got a whole bunch of register pressure in the middle of another function that also had a whole bunch of register pressure, because now you may have a lot more spilling. Loop invariant code motion was something that Guofu brought up, that in that case you may be moving something out of a loop, but doing that creates a register that's going to a live range that's going to span the whole loop, and it might actually be cheaper to rematerialize the value in some fashion inside the loop, so that then you don't have to maybe spill somewhere else in the loop. Another one of the areas I've messed around with over the years is parallel reassociation, which is the idea that we have an expression where you're adding up 15 things or something, that instead of just serializing the whole thing, you split it into two or more chains that are parallel that are just added together, or whatever the operation is, it's done at the end, and then you can make use of multiple functional units to do the computation. But the downside is that it multiplies the number of registers used in evaluating expressions. So it's not a good idea to do it if it's in the middle of some loop that has a lot of register pressure as well. And then another obvious case is loop unrolling might want to be sensitive to this, because if you could go backwards by unrolling and then discovering that in order to get the unrolled loop you have a whole bunch of spills. The current only analog we have for this, I mean, the analog that we have for controlling things like inlining is just looking at pure code size. But pure code size, there's a lot of differences between things that could have the same number of instances, but could have a small amount of register pressure or a lot of register pressure, or just a small amount of complexity in terms of basically the number of interrelated expressions in the code.
Yeah.
And so it's not necessarily a good analog for this.
Like if you do loop unrolling by factor of n, then you grow the number of registers needed by factor of n, sort of. While for other things, like if you do inlining, you do grow the number of registers needed, but not so quickly at all.
Yeah, and while we have the TreeSSA Live module, the problem with using it in these kind of contexts is that it assumes that that it could just scan the IL and get the data it needs. And by the time we reflect a loop unroll into the IL, that's kind of too late. We want to know, essentially, if I unroll this loop, what's the register pressure going to look like? Am I increase it by a factor of 2, or is it a small delta? And the TreeSSA Live module can't really deal with that kind of. Give me an analysis without actually reflecting it in the IL.
Yeah, the actual enrolling is done on RTL level.
Yeah, but so yeah, set that aside. Call it inlining or LICM or whatever, whatever transformations out there that we care about.
But please let me finish. At RTL level, we know about registers, but at tree level, at Gimple level, we do not really know about.
No, but you use SSA names as a proxy. So do I now have at any given point 5 times more SSA names that are conflicting? Because that's what it computes.
But that's not a very good proxy.
It's a much better proxy than we got now, which is nothing.
It's much better.
Yeah.
It's an order of magnitude better, but the structure of TreeSSA Live is not amenable to the kind of analysis that I think we want to be doing here, in that it has to read the IL. And what we want to know is, what is this transformation going to do to the pressure at given points?
So one of the issue of doing all this on SSA is that we don't really have any fixed schedule of the SSA devs on Gimple, because any estimate, like if you throw the TreeSSA Live on a basic block, it will compute something. But then at RTL expansion we have TER, and it will produce a completely different schedule with a completely different register pressure characteristic. So it's absolutely.
And there was the work from Bear several years ago to try and add a scheduler into that phase that never really went anywhere. But conceptually, TER is part of the problem here, in that it can, as Richie says, it changes the schedule and can dramatically increase register pressure as it builds these bigger expressions. And that's really all a symptom of the problem that in the past, the expanders had a fair amount of optimization smarts in them. And that was because this is pre-Gimple, pre-TreeSSA. And so we wanted to create these big expressions that we could hand off to the expanders. So to solve that, you probably got to stop that.
Yeah. So I think. So yeah, I think.
Smart, and they're not actually very smart. They actually degrade code quality a lot. Expanders do way too much.
Yeah, so that's true. So I think 2 or 3 years ago, I looked at this, like after Bernd looked at this like 5 years ago, and I tried to turn off the TRR, or better reflected on Gimple itself. But then there's a lot of code quality regressions with not doing the smart expanders that are not so smart, but apparently they have some smartness that is not there otherwise.
Right, definitely. They do quite a bit of stuff that is not done anywhere later.
Yeah.
So,
yeah. So we've got to solve that. That's one of the sub problems we have to solve here if we're gonna really do this.
But
TER has to go, but we have to solve the expander problem.
Yeah. So what I don't actually understand from you said that the register pressure is a problem with inlining, but if you don't inline, you have to spill around the call, and if you inline, you can spill around the inlined block boundary in exactly the same way. So why is it increasing the spilling if you inline?
Well,
you could increase comic sub-expression finding that will increase register. There's ways it can happen. It's not a direct one-to-one correlation.
It's partitioning the problem so that by not inlining, you're partitioning the problem, and the register allocator does not have to deal with the whole thing at one lump. It may do a better job in that case.
Okay, so but I think it does this right now. It's the partitioning into areas of loops, and so that's one thing that should be fixed in the register, in the allocator. So by partitioning the function into interesting regions, and not by not inlining,
or even splitting at RTL level some code into some functions. If there's a good chance that it will improve the register allocation.
Yeah, but so it's just partitioning the function into regions. If you call that functions, okay, but yeah, making the register allocator work on regions in a better way than it does now.
Yeah, well, its model right now is it builds regions based on loop structure, and that may not always be the best structure for these scenarios. So yeah, I agree, Richie, that having alternative ways of partitioning the IL is probably part of the solution here as well.
Yeah. So what I was also thinking is the loop in variant motion, and in particular the load store motion, which include the loop carried registers. If there's a way, if we just do it as aggressively as we do now, but a way to undo parts of the harmful transforms before expanding to RTL, just in response to register pressure, to not lose like vectorization, which absolutely requires to have all the loop store motion applied, because it otherwise can't vectorize reductions, right? So if there's a way to more intelligently undo the transforms, and instead of doing it by spilling, by rematerialization, which I understand in theory, a register allocator can also do the rematerialization, but of course it's much more difficult to see where to rematerialize from than like if we would try to do this on Gimple.
Yeah.
The register allocator can never create good code if you overwhelm it. It will go to reload, it spills off, right? And that is never ever good code. It cannot be. It's correct code. That's what reload does. But it cannot be good code. So you really have to make sure to not have too many pseudos, or the diameter of code, or whatever you want to call it.
So I almost hesitate to mention it, but does this start to feel like another phase of lowering as we go from Gimple to RTL? So in that phase, as we're moving RTL, we could start querying the back end. How many registers do you have? oh shit, I'm asking for 193 live things at this point. And you only have 32 registers. Well, that's clearly not going to work.
And it's not just how many registers you have. You know, you may only do one subset. For example, MIPS has the multiply instruction that.
Yeah, I was thinking in terms of per class.
And PowerPC is AltiVec versus VSX registers.
Yeah, you have to break it down into the chunks that are useful and where things are likely going to end up. But the basic concept or the basic question I was starting to ask is a piece of this an expansion problem? Where do we drive trying to split ranges or undo optimizations as part of the lowering phase as we go from GIMP to RTL? Does that make sense?
We already do some of this. I think we have this uncopy propagation paths, which basically tries to remove copies from constants on edges, right?
Yeah, that was strictly a code size thing. I'd like to see that go away. I wrote it. It's not very nice.
But it's effective. So and we do have, like, in the out of SSA phase, we do have like also some tricks to improve the RTL expansion. And yes, so we are already doing some lowering. We are doing the vectorized and cont expression stuff with the instruction selection, and we are using more internal functions that directly map to optabs. So I think we are walking in the direction to do a lot of the RTL expansion on Gimple itself and exposing, like, the actual the actual code via the internal functions. And yes, and the important step when we want to have an estimate on register pressure is indeed to get rid of TER. So to have the magic that Expand is doing right now be done on Gimple in some way. And when I remember correctly, most of the regressions are in the area of expanding memory accesses, so bit field extract and stuff like that. Because there, it's like if you have like an add of 2-bit extracts that gets magically combined into magic, and that's no longer happening if you just expand the bit extract, then the add, and then the other. So So some of this stuff has to be done before actually expanding to RTL.
Actually, I would like to add that global register allocator have Notion regions, and as you told, currently it's only loops, but it can be easily extended to other regions. The only requirement that the regions should be nested, and that's it. So maybe somebody could pick up this project and do this. Another problem with still you can split on region borders, but you cannot, for example, move or rematerialize instruction in the region. There is rematerialization. It's in the local register allocator, but it's very constrained path because we already assigned register, and when you have pseudo register, rematerialization would work much better. Actually, I remember I implemented before the new register allocator the second part of Simpson thesis about global value numbering, and second part is about rematerialization, how to do rematerialization on SSA level to decrease register pressure. So this could be done in the middle end, I guess. And that time it gave 1% improvement on spec int 2000. So again, register immortalization in register locator is very constrained, and there is few chances to make rematerialization, and it's better to do this before assigning registers. So that's my proposal.
So when you say this should be done in the middle end, do you mean at Gimple or at expand time actually?
It could be done on RTL level, it could be done on SSA level. It's better to do this on SSA level. Actually, Simpson thesis was all about SSA. It's easier to do this optimization on SSA level. The problem is, again, how to evaluate register pressure.
Well, and that's why I was leaning towards that Gimple to SSA, or sorry, Gimple to RTL border, because that is a fine time to introduce the concept of register pressure based on what the target, based on the target register set. I don't think we want to try to do that earlier, because
if you want to do it at expand time, you need to make more subpasses at expand time. We actually already need that.
Yeah, I think it's already a requirement.
Yeah, but this would be a really good excuse to start doing that.
Yeah, I agree, Secker.
Yeah, so I explicitly talked Martin into naming the cont expression expansion pass Gimple instruction selection, because that should be the kitchen sink to move the magic of expand to, so that expand really can just be the dump Gimple to RTL expander via optabs. And
yeah, it should be just a very simple lowering. What
Yeah.
we're doing in that expansion phase is way too complex.
Right, it will stay very complex because it's very much it's very big impedance mismatch between Gimple and RTL. So it will stay complex, but it doesn't have to do all these extra things that it does.
Yeah.
Right. I think we need to evaluate all those extra things and start moving them either into the Gimple SSA optimizers, which I think that's where probably most of them want to live. There may be some that move into the RTL space, but I think most move into the Gimple stage. And what's left is really a lowering phase as opposed to an optimization and lowering.
Yeah. Right. So it's if you want to do an experiment, you can just turn off TER completely and then look at the test suite, and you will see test cases that will start failing because we don't optimize them anymore, and then see what is necessary to recover the expand magic in a lowering phase that happens before RTL expansion.
Yep, that would be the exact way I would start that. And I always wanted to do that and just never found the time.
It's quite a big task, at least to get to a point where we can really disable TER.
Yeah, I'm sure it's going to be the case where somebody spends a year on this, just finding all those dusty corners that we've ignored for the last 2 decades. But that's really what's happened here. Is that code is 2+ decades old. We never went back and really revamped it when we introduced SSA.
So the good thing is that we now have the pass that runs over the whole IL before RTL expansion, just for the cont expressions, and you can just add to that. And it's not that you have a patch that just looks for one very special case and doing an extra IL walk, because you can just piggyback on the existing one. So there's no excuse to not do it.
Well, the excuse is time.
Of course.
Well, one issue I'll mention though is even at expand time, and actually even during register allocation, we don't have exact register pressure counts with like union register classes and that. The problem is because we don't do instruction selection until during register allocation. So we don't know whether some pseudo is going to end up in a GPR or an FPR or vector register sometimes, that has these large kind of union register classes.
Absolutely.
Yeah.
I think a lot of this, at least in my mind, is trying to cache the pathological cases where the GIMPL SSA optimizers are giving the back end code that has pressure that is so high that there's not going to be a way to allocate without spilling. I'm trying to deal with the pathological cases as opposed to kind of squeezing out the last bit of performance, because we do have a lot of pathological cases still.
Yeah, as I understand, expander only increases register pressure. So if you can evaluate register pressure before expander and it's high, you need to do this in any way, even if expander is ideal and will not increase pressure. So
if you can avoid the pathological cases, it gives us more latitude to be a little bit more aggressive in some of the other tunings of the compiler, because we're not so worried about keeping from just catastrophically bad performance in those cases.
Exactly.
yeah, the problem with register classes also that we have a lot of architectures with regular classes. So global register allocator is trying to do some approximation and build register classes non-intersected. It's called pressure register classes, and these classes are used in register pressure sensitive optimization in RTL. It's instruction scheduling and loop invariant motion mostly, and still it's working. So it's still improving code, although the approximation is not exact. You will never have exact approximation of register pressure when you have irregular register files in your target architecture.
Yeah, but it shouldn't be too hard to not be off by a factor of 2 or more, which we actually are now. So
yeah, it's approximation is still working, and before the new register allocator, we had no at all register pressure evaluation. And when I implemented the new register allocator and implemented this infrastructure for approximate evaluation of register pressure, it became used in couple optimization, like as I told, instruction scheduling and RTL loop invariant motion. So to have something is better than nothing.
sure, yes.
So we've kind of taken over this. Aaron, are you getting what you want out of this?
Oh, absolutely. This is a ton of engagement, and we're headed in the right direction, which is discussing, some things which are gonna help this problem generally, I think.
Okay, I just want to make sure that you didn't have other aspects of this you wanted to dive into. So we can keep going. It's fine with me.
No, I mean, the way I see what happened here is that, I had an idea of, well, let's have some infrastructure to figure this out. And I think what we have actually come here is, well, maybe some of what we actually do at Expand should be done earlier. And that is maybe even better.
I think it's a prerequisite to solving the problem you're trying to solve. At least that'd be my position.
So there's definitely like places on GIMPL optimizers like the loop invariant and store motion, where we could use very, very simple heuristics like ask the target how many integer or floating point registers you have, and not create like 200 loop carried register dependency. That's something what we currently don't do, which we can easily do either just very stupidly by a new param, never generate more than 20, and if PowerPC thinks 30, then well, they can change it to 30, or just I guess it must be available, like the size of the register classes must be accessible somewhere, even on Gimple. So to use those as some, but
yeah.
as I mean, it can happen that in other pathological cases, you then fail to vectorize, which would have reduced the register pressure by a factor of 16 again, because it was all character loop carried dependencies, and they would all fit in a register, in a vector register. So there's always downsides to these kind of heuristics when you apply them too early.
Actually, sorry, Sarah.
Whenever you vectorize something, it ends up in different registers. And all of our vector registers are the same registers, so the rest of the mode class doesn't matter at all anymore. So,
I should say that there is already some approximation in building non-intersected register classes in global register allocator, which can be used for register pressure calculations. It's called pressure classes, I guess. If you look at into the global register allocator, you will find this. It doesn't depend on.
that is the one that targets can set directly, right?
Yeah, it's from. It's calculated from machine dependent descriptions. So you just need now to make a map or correspondence between this given pseudo register to given pressure register class, and you can calculate, and you know how many registers you have in pressure register class, and you will see is there is register pressure excess, and you need to do something with this. But how to make correspondence between register pressure class from given pseudo to register pressure class, it's another issue. I guess it could be done only by mode of pseudo register.
For the parallel reassociation, wouldn't a possible solution be try to undo it at RTL time after computing the pressure? Because undoing what the reassociation did and trying to serialize it, if the pressure is high, shouldn't be that hard.
Yeah, I think that one's relatively straightforward conceptually, and I think the loop invariant code motion is relatively straightforward, because when we do loop invariant code motion, we're essentially creating conflicts for the entire duration of the loop. So if we create 200 invariants for one loop, we just created 200 conflicting objects for the entire duration of that loop. So I think those two are kind of simpler to understand how or where we put our tweaks. The inlining one, I think, is a lot tougher, just because it's much harder to predict how inlining is going to affect the pressure problem.
Yeah, quite often inlining reduces the pressure.
Often it would. I just think it's a lot harder to predict. Whereas predicting LICM or understanding how to undo reductions or reassociation, that stuff, I think we know how to do that. That's easier. It's easier to analyze. It's easier to rewrite. Inlining, I don't have a solution for.
I wouldn't even think about inlining before tackling all the other issues.
You're probably right, Richie. See where we are after we tackle the other stuff.
Yeah, or if you want to tackle that, try to look at what Vlad said and extend the kind of regions the global register allocator forms into some.
The region seems like a good idea there. Like, I mean, right now we do loops, right? But what if you what if you identified strongly connected components or something like that and tried to partition things into pieces like that?
Yeah.
Yeah, I think regions probably would really help in the allocator. The thing I would caution against, I had a long discussion with the SGI guys many years ago, and they were in the process of trying to essentially take their entire back end and make it region based. And they worked on that for like 5 years and never got it to work. So I could see us doing it in a much more constrained form. We are going to focus on the allocator and do it there, but I wouldn't suggest we try to plumb that all the way through, because I think we'll end in the same boat there they ended up in. We'll spend a lot of time and never actually get it working.
Yeah, building new regions solves register leaf splitting problem, but it doesn't solve, for example, a rematerialization problem. As I told, we have rematerialization. It's in local register allocator, but it has very constrained conditions to work, because we already assigned all register, and we cannot move this particular instruction through instruction which uses the same registers, so hard registers. So I guess at least register rematerialization should be done before a register allocator, where it could be done in the middle end, or it could be done right before register allocator. But
I think history would tell us we'll end up with both.
Yeah, it could be done at both. Yeah, the same with like loop invariant code motion. We have it in the middle end and on RTL level. But on the RTL level, we have register pressure sensitive loop invariant code motion, but not in the middle end.
Yeah, we also have the scheduler. I mean, the first scheduling pass, I'm always thinking that one could do a lot more things. I'm not sure if anybody ever did rematerialization within the scheduler.
I don't know, Richard. I don't think so. Register instruction scheduler is so complicated, so I don't think so.
But register allocation is even more complicated. No?
Well, I think there's a lot of pieces of the scheduler that can help us. Like all the dependency analysis, for example. So I wouldn't necessarily try to do it within the scheduler as written, but I think there are pieces of the scheduler that we could carve out and say this is generic enough to allow us to build around it. The other question you had is, has anybody ever tried it in the scheduler? I don't think anybody's ever done rematerialization in the scheduler. I'm not aware of anybody ever experimenting there.
Yeah,
not with our tools.
The main purpose of scheduler is move instruction, not to rematerialize this. So I don't think so. It's complicated, the current instruction scheduler. Even if you look at scheduler from Institute of System Programming of Russian Academy, it's even more complicated. So,
if you want to change anything in Scat1, the first thing you should do is make it select which variant of instruction to use, because it matters more than anything else.
Yeah, our long-standing instruction selection problem.
Right.
Yeah, I forgot we actually have modular scheduling too, and it's register pressure sensitive. Yeah. But nobody use it, unfortunately.
It doesn't work very well, and that's because no one uses it. So
because it's doing a bad job. Yeah, I agree.
Well, I mean, again, it doesn't have the information that it needs. The problem is that it doesn't have the actual final selection of instructions to be able to create the optimal schedule.
Yeah, Yeah, this is a specific problem of GCC because we we have a special machine description which forces us to use instruction selection. Do this. Yeah,
exactly.
But on the other hand, as it was discussed recently, it makes passes after register allocator is much simpler than, for example, in LLVM. When in LLVM you choose a particular instruction alternatives, and after assigning registers, it's different. You need to do a lot of work to fix this code, and it's hard to formalize. So there are some consent pros for GCC approach.
So I've been keeping notes in the shared note space. I don't know if I captured everything, if there are other ideas that we want to try to, in addition to the great, summary that Aaron already created here, questions. Yeah, 5 minutes left.
There is one question raised by Chip. I don't think we've answered yet.
I was always, I'm actually like since a few years looking for a place to introduce AI into GCC. But I didn't think about register pressure, but about the splitting of the function into regions for the register allocator. We could throw an AI on that, because it's probably going to be a bunch of heuristics or just use the strongly connected components, but that's basically what we're doing right now with the loops.
I'm pretty skeptical about using artificial intelligence in compiler field. That's just my opinion. Yeah,
you know, that's we had a whole other research topic.
Yeah, we had what is called post-mile project from Friends Academy in RIA. And it gave nothing actually, and they just this project was transformed to collecting test samples and how these test samples behaves when different set of options are used. So I don't see that artificial intelligence works well in compiler field. It's different problem, I guess. It's not computer vision or something. It's very non-smooth function minimization, and it doesn't work for compiler field. Actually, I tried to use myself artificial intelligence approaches many times for GCC, and always it didn't work.
Well, at least some of the issues look like pattern recognition to me, like splitting a function into allocation regions. It looks like pattern recognition.
I think, maybe in the constrained environment that we're talking about, there might be something there, Richie. I kind of like my other comment. I would recommend against trying to solve the bigger problem with AI. I know Uli was looking at this, Uli Trepper, and it went nowhere. But in a constrained thing, how do we partition for the register allocator? That might be small enough that it's worth an experiment.
Well, at least it would be cool, right, to have a production compiler using AI.
Yeah.
Well, but I think there are some heuristics to think about in that space. There's strongly connected components, there's loops, there's hot and cold code. There are things to look at there.
Yeah.
Sure. But but where, which ones are important? I don't even think we really know which ones would end up being important.
For example, switch statements also, where one thing of the switch uses lots of registers and everything else doesn't use much. Basically, Perl Bench in CPU 2017.
Oh, the irony! I'm looking at Perl Bench right now. It's on my screen.
Bill raised his hand. Bill, do you have a question? Bill Schmidt.
Can you hear me now? Yeah, there
Yeah.
we go.
Yes.
My mic wasn't working. I apologize. I have a request. This has been a really excellent exchange of views. I would hate for this to get lost. Could we see some of this discussion put out on the wiki and a pointer to it put in the GCC mailing list, and people can go out there and continue the discussion? Or is there a better way for this to move ahead? I think we
want to capture it, certainly. And I think David has at least got a capture of the discussion, so we just need to move that out into a more public place.
Yeah. Let's just make sure we don't lose it, because I think this was a really, really good topic and really good discussion here. Thanks.
All right, I think we are
Thanks, everybody.
At the end of our time. So thank you, everyone. Thank you, Aaron, Michael, and Cedar, and Jeff and Vlad participating in the discussion as well. So this wraps up the GNU Tools Track at LPC. So I'd like to thank the organizing committee, which is Jeremy Bennett from Embecosum, Joel Rebecca from Adacore, Sarah Cook from Embecosum, program committee, which is Jeremy, Joel, David Edelson, Frank Igler, Jose, and Ulrich. And the session chairs, Jeremy, Joel, David, Jose, and Ulrich. Thank you all. And Sarah, do you have the sponsors? I'd like to thank our sponsors as well.
You should have the slide control, and you should.
Oh, I do.
There you go.
All right. Our diamond sponsor is Facebook, and our platinum sponsor is IBM, and the gold sponsors is ARM and Microsoft, and silver sponsors AWS, Netflix, and Red Hat. And the speaker gift sponsor is Collabora, and t-shirt sponsors VMware. And we'd like to also thank the Linux Foundation for the conference services. And to wrap up, we have the anti-harassment policy. I think everybody is aware of this after 4 days. And I guess that's it. Thank you all. There are some microconference sessions tomorrow, but thank you for your presence and participating in the conference. Hope to see you all next year. Sarah or Jeremy, do you guys have anything else to add?
No, just a massive thank you to all the speakers for your support in helping run this. Thank you to the committee. Fingers crossed, I will see you all next year in person.
That is the hope.
Yeah. See you at Cauldron next year. See you at Cauldron. Thanks, everyone. See you
I think we said that last year.
I know. I think it's really good. We're going to really try and make it happen this year.
Yeah. All right. Thanks, everyone.
Thank you. Bye.
Thanks. Bye.